Reality encompasses everything that exists the physical universe, with its matter and energy, the dimension of time through which events unfold, the laws of physics governing interactions, and potentially realms we have yet to discover or comprehend. For most of human history, reality seemed eternal and unchanging in its fundamental nature. The stars wheeled overhead in endless cycles. The earth endured. Time flowed without beginning or end. But modern physics reveals a different picture. Reality had a beginning 13.8 billion years ago in the Big Bang. Space itself expands. Stars are born and die. Even the vacuum of space seethes with quantum fluctuations. Nothing about reality appears truly permanent when examined closely. The question of whether reality can end forces us to define what we mean by both reality and ending. Philosophers distinguish between existence itself and the particular forms existence takes. The heat death of the universe, where all stars burn out and matter decays into a thin gruel of particles at near absolute zero, represents an end to interesting processes, but not annihilation of existence. The universe continues, just in a maximally boring state. True ending would mean existence itself ceasing not transformation, but termination. Whether such absolute ending is possible remains deeply uncertain because we cannot observe or experiment with non-existence. Every test we perform presupposes existence. We are trapped inside reality, trying to understand its boundaries from within. Physics provides multiple scenarios for reality's potential endpoints. The second law of thermodynamics guarantees that entropy disorder increases over time in closed systems. Applied to the entire universe, this implies an eventual heat death, where all energy disperses evenly and nothing further can happen. Quantum mechanics permits vacuum decay, where space itself transitions to a lower energy state, destroying everything in an expanding bubble traveling at light speed. Cosmological observations show space expanding at an accelerating rate driven by mysterious dark energy, potentially leading to a big rip where expansion tears apart galaxies, stars, atoms, and even space-time itself. Each scenario describes reality not ending, but transforming into states we would not recognize as reality. The concept of reality running out implies depletion of some resource or capacity. In thermodynamic terms, the universe runs out of free energy available to perform work. Once entropy reaches its maximum value, all energy exists in equilibrium states where no gradients drive processes. In information theoretic terms, the universe might run out of computational capacity if reality is fundamentally a simulation or mathematical structure limited by processing power. In quantum mechanical terms, reality might exhaust possibilities as wave functions collapse and quantum superpositions resolve into definite states. Each framework suggests different resources that could be depleted, leading to different types of endings. Time itself might end, rather than continuing forever. General relativity permits spacetimes with temporal boundaries, singularities where time ceases to be defined. The Big Bang represents a past temporal boundary. Future singularities might arise in scenarios like the Big Crunch, where the universe collapses back on itself, or the Big Rip, where expansion becomes infinite in finite proper time. If time ends, asking what happens afterward becomes meaningless. There is no afterward. Duration itself terminates. This represents perhaps the most profound type of ending, not transformation to a different state, but cessation of the framework in which change occurs. Observable evidence constrains, but does not eliminate these scenarios. The universe's measured flatness, expansion rate, matter density, and dark energy density all inform predictions about its ultimate fate. Current observations favor eternal expansion, with the universe growing progressively colder and emptier over timescales exceeding 10 to the 100th years. But measurements contain uncertainties. Dark energy, comprising 68% of the universe's energy budget, remains poorly understood. Its properties might change over cosmic time. New physics might emerge at energy scales or distances beyond current accessibility. The universe might contain elements or dimensions we have not yet detected. Our predictions extrapolate current understanding across vast temporal and spatial scales where different physics might govern. The question of whether reality can end ultimately probes the nature of existence itself. Does existence necessarily imply persistence? Must something that exists continue existing, or can existence cease? Quantum mechanics demonstrates that virtual particles constantly pop in and out of existence. But do they truly cease to exist, or merely transition to unobservable states? Conservation laws in physics suggest that certain quantities, energy, momentum, electric charge, cannot be created or destroyed, only transformed. If reality conserves some fundamental quantity, it might be unable to end completely. Alternatively, reality might be an emergent phenomenon arising from something more fundamental, capable of dissolving back into that substrate. These deep questions transcend current physics, reaching into metaphysics and philosophy, where empirical evidence gives way to logical reasoning and conceptual analysis. The observable universe has boundaries. The observable universe extends only so far, approximately 46.5 billion light-years, in any direction from Earth, giving a diameter of 93 billion light-years. This distance exceeds the 13.8 billion light-years one might expect from multiplying the universe's age by the speed of light, because space itself expanded while photons traveled toward us. Light emitted from distant galaxies when they were much closer has been traveling for billions of years, but during that journey, space stretched, carrying the source galaxies to their current vast distances. The observable universe contains everything we can ever hope to observe using light, gravitational waves, neutrinos, or any other signal traveling at finite speed. Beyond this boundary lies the unobservable universe regions, from which light has not had time to reach us. The particle horizon defines the observable universe's edge, the maximum distance from which light could have reached us since the Big Bang. This is not a physical barrier, but an informational boundary imposed by the finite speed of light and finite time since the universe's beginning. Galaxies beyond the particle horizon exist but remain invisible because their light has not arrived yet. As the universe ages, the particle horizon expands, bringing previously unobservable regions into view. However, accelerating cosmic expansion driven by dark energy introduces a complication. While the particle horizon expands, an event horizon simultaneously exists, a distance beyond which events happening now can never be observed in the future, because expansion carries those regions away faster than light can cross the intervening space. The cosmic event horizon, located approximately 16 billion light-years away, given current expansion rates, marks a more ominous boundary. Galaxies beyond this distance are receding so rapidly due to accelerating expansion that light emitted from them now will never reach Earth, even given infinite future time. Expansion continually carries photons farther away faster than they approach. These galaxies permanently exit our observable universe. Currently, about 95% of galaxies we observe lie beyond the event horizon. We see them as they were billions of years ago, when they were closer and inside the horizon, but they are lost to us now. Their current states and future evolution will forever remain unknown. We are watching ancient light from objects that have effectively ceased to exist from our observational perspective. Within the observable universe, we count approximately 2 trillion galaxies. each containing tens of billions to hundreds of billions of stars. The total number of stars exceeds 10 to the 24th, a trillion. These are conservative estimates based on deep field surveys like the Hubble Ultra Deep Field, which revealed thousands of galaxies in a patch of apparently empty sky smaller than a pinhole held at arm's length. Extrapolating across the entire sky yields the 2 trillion galaxy estimate. The James Webb Space Telescope, observing infrared light, detects even more distant galaxies from when the universe was only a few 100 million years old. Each new observation refines our census, generally finding more galaxies and stars than previous estimates suggested. The observable universe represents an infinitesimal fraction of the total universe if inflation theories are correct. During cosmic inflation, a brief period of exponential expansion lasting from roughly 10 to the negative 36th seconds to 10 to the negative 32nd seconds after the Big Bang, space expanded by at least a factor of 10 to the 26th. This tremendous growth stretched the universe far beyond what we can observe. Estimates suggest the entire universe is at least 10 to the 23rd times larger than the observable portion in volume, and potentially infinite. If the universe is infinite, the observable portion represents 0% of the total, an infinitesimal bubble in an endless expanse. Everything we see, every galaxy and star, constitutes just our local neighborhood in an incomprehensibly larger whole. This raises profound questions about reality beyond our horizon. If space extends infinitely, logic suggests infinite repetition. With infinite volume and finite types of particle arrangements, every possible configuration must occur infinitely many times. Somewhere beyond our horizon, exact duplicates of Earth exist with duplicate versions of you living identical lives. Such duplicates would be separated by incomprehensible distances. Estimates suggest roughly 10 to the 29th meters to the nearest Earth duplicate. These duplicates would be fundamentally unobservable, lying far beyond our event horizon. They exist in a parallel but forever disconnected reality. The concept strains comprehension. Infinite versions of you having this exact conversation, alongside infinite versions making different choices at every decision point. The boundaries of the observable universe are not fixed but dynamic. The particle horizon expands as the universe ages, continually bringing new regions into observability. However, the event horizon tells a grimmer story. As dark energy drives accelerated expansion, the event horizon contracts. Fewer and fewer regions remain observable in the long term. Distant galaxies we currently observe will one day redshift beyond detection as they cross the event horizon, vanishing from view. In 1 trillion years, observers in the Milky Way will see only a few dozen galaxies in the local group, gravitationally bound together. The rest of the universe will have disappeared beyond the horizon. Future astronomers will observe an apparently empty cosmos, devoid of evidence for the Big Bang, cosmic expansion, or the 2 trillion galaxies we see today. Observational reality shrinks even as the universe expands. Space expansion and vanishing galaxies. Space itself expands, carrying galaxies apart like raisins in rising bread dough. This is not motion through space, but growth of space itself, described by general relativity's solutions for a homogeneous universe. The expansion rate, quantified by the Hubble constant, equals approximately 70 kilometers per second per megaparsec for every 26 million light-years of separation. Space expands by 70 kilometers per second. At sufficiently large distances, this expansion velocity exceeds the speed of light. Galaxies separated by more than approximately 14 billion light-years recede from each other superluminally. This does not violate special relativity because nothing moves through space faster than light. Space itself grows, carrying distant objects along for the ride. Edwin Hubble discovered cosmic expansion in 1929 by observing that distant galaxies show redshifts proportional to their distances. Light from receding galaxies stretches to longer, redder wavelengths as space expands during the photon's journey to Earth. The farther the galaxy, the greater the redshift, indicating faster recession velocities for more distant objects. This relationship, known as Hubble's law, provided the first direct evidence that the universe expands. Initially, astronomers believed expansion was decelerating under gravity's influence, eventually halting or reversing into contraction. This expectation persisted until 1998, when observations of distant supernovae revealed accelerating expansion, a discovery that earned the 2011 Nobel Prize in Physics and upended cosmology. Accelerated expansion is driven by dark energy, a mysterious component comprising 68% of the universe's energy density. Dark energy's nature remains one of physics' deepest puzzles. The simplest model treats it as Einstein's cosmological constant, a constant energy density inherent to space itself. As space expands, more space forms, creating more dark energy while matter density dilutes. Dark energy's density stays constant while matter thins out. Consequently, dark energy's gravitational repulsion strengthens relative to matter's attractive gravity. Approximately 5 billion years ago, dark energy became dominant, and expansion began accelerating. Acceleration will continue increasing if dark energy behaves as a cosmological constant, driving expansion rates toward infinity over infinite time. The accelerating expansion creates cosmic event horizons boundaries beyond which we lose causal contact with distant regions. Light emitted now from galaxies beyond the event horizon, located approximately 16 billion light-years away, will never reach Earth. Expansion carries these galaxies away faster than photons can approach through expanding space. We currently observe many such galaxies because we see ancient light emitted billions of years ago when they were closer and within reach, but their present states are forever hidden. Any events occurring there now, supernova explosions, galaxy mergers, potential civilizations, cannot affect us, nor we them. These regions effectively cease to be part of our universe in any operational sense, cut off by expansion as surely as if separated by an impassable barrier. Approximately 95% of galaxies currently observable will eventually vanish beyond the event horizon. Their light will redshift progressively toward longer wavelengths, becoming dimmer and dimmer as photons lose energy climbing out of space's expanding potential well. Eventually, photons redshift to undetectably long wavelengths, radio waves, stretching to wavelengths larger than galaxies, then larger than the observable universe itself. The galaxies do not physically disappear. They continue existing, evolving, perhaps developing life and civilizations. But they fade from observability, crossing an informational event horizon as irrevocable as a black hole's event horizon. Once beyond, they are gone from our reality forever. The timeline of cosmic isolation stretches across trillions of years, but follows predictable stages. Within a few billion years, the most distant galaxies currently visible will fade beyond detection, their light too redshifted to observe. Within hundreds of billions of years, all galaxies outside the local group, the Milky Way, Andromeda, Triangulum, and a few dozen dwarf galaxies gravitationally bound together, will have vanished. The local group itself will merge into a single, massive, elliptical galaxy through collisions and mergers. Observers in this far future galaxy will see only their own galaxy surrounded by darkness. The cosmic microwave background will have redshifted beyond detection. Evidence for the Big Bang, cosmic expansion, and the existence of billions of galaxies will have disappeared. Future cosmologists will observe a static, isolated universe. This scenario raises disturbing implications for the nature of observational reality. If observations define reality, then galaxies beyond our event horizon effectively cease to exist for us. We cannot affect them, they cannot affect us, and no future observation can ever reveal their current states. In what sense do they remain part of our reality? Operationally, they do not. Philosophically, most physicists assume these regions continue existing independently of observation, but this assumption cannot be verified. We are trapped in an expanding bubble of observability, watching the wider universe slip away beyond reach. The cosmos we observe is not the whole cosmos, but a limited, shrinking window into a vastly larger and largely unknowable reality. Existence extends beyond observation, but observability contracts despite existence's expansion. Time has a direction and arrow. Time flows in one direction from past to future, defining what physicists call the arrow of time. We remember yesterday, but not tomorrow. Eggs break, but never spontaneously reassemble. Stars burn fuel and cannot unburn it. Entropy increases, but never decreases. These observations seem obvious from everyday experience, yet the fundamental laws of physics, Newton's mechanics, Maxwell's electromagnetism, Einstein's relativity, even quantum mechanics at the particle level are time-symmetric. They work equally well running forward or backward. If you filmed atoms colliding and played the video in reverse, the reversed motion would obey the same physical laws. So why does time appear to flow in only one direction at the macroscopic scales we experience? The second law of thermodynamics provides the answer. Entropy, the measure of disorder, or the number of possible microscopic arrangements consistent with macroscopic properties, always increases in closed systems. This statistical tendency defines time's arrow. Low entropy states are rare and highly ordered. High entropy states are common and disordered. Systems evolve from improbable to probable configurations. We define the past as the direction of lower entropy and the future as the direction of higher entropy. Memory works only in one direction because creating records requires organized low-entropy structures that leave traces. High-entropy scrambled states carry less information about their origins. The puzzle deepens when we trace entropy backward to the Big Bang. The universe began in an extraordinarily low entropy state, all matter and energy, compressed into a tiny volume in a highly organized configuration. Subsequent evolution has steadily increased entropy as structures formed, stars ignited and dispersed energy, and gradients dissipated. The universe's current entropy, while immense, remains far below maximum. We exist during a special epoch where entropy is intermediate, high enough for complexity, but low enough for structure. But why did the universe begin with such low entropy? The second law explains entropy increase, but cannot explain the initial low entropy condition that started the clock. Various proposals address this initial condition problem. Inflationary cosmology suggests that exponential expansion flattened and homogenized the early universe, creating uniform low-entropy conditions. The Hartle-Hawking no-boundary proposal argues that the universe's origin in imaginary time naturally yields low entropy. Some cyclic models posit that each cycle begins with low entropy following a bounce or transition from the previous cycle. The anthropic principle suggests we observe low initial entropy because only such universes permit complex structures like observers. Each explanation remains speculative, highlighting that our understanding of time's origin and direction remains incomplete. The arrow of time might behave differently in the far future. In heat death scenarios, where entropy reaches maximum, time's arrow becomes meaningless. With all energy at equilibrium and no entropy gradients, nothing distinguishes one moment from another. Time continues existing as a parameter in equations, but no changes occur to mark its passage. Past and future become indistinguishable in this eternal, featureless present. Alternatively, in a big crunch collapse, one might expect time's arrow to reverse. However, Calculations show entropy continues increasing even during contraction as matter heats up and structures collide. Time's arrow persists pointing toward higher entropy, regardless of whether space expands or contracts. In scenarios like the Big Rip, where expansion tears apart space-time itself, time might end entirely. General relativity permits singularities points where space-time curvature becomes infinite and time ceases to be defined. Future singularities would represent temporal boundaries beyond which time does not exist. There is no after such a singularity because time itself terminates. This represents perhaps the most profound ending, not transformation but cessation of the framework in which change occurs. Whether quantum gravity effects prevent such singularities by replacing them with bounces or transitions remains unknown. The arrow of time, and perhaps time itself, might reach a final boundary where reality's temporal dimension ends. Entropy, the universe, march to disorder. Entropy quantifies disorder, or the number of possible microscopic configurations consistent with a system's observable macroscopic properties. Ludwig Boltzmann formulated this precisely in the late 1800s. Entropy S equals the Boltzmann constant K times the natural logarithm of the number of microstates. A gas with molecules randomly distributed throughout a container has higher entropy than the same gas confined to one corner because vastly more molecular arrangements correspond to random distribution. The second law of thermodynamics states that entropy never decreases in closed systems. It either increases or, in idealized reversible processes, remains constant. This law introduces time asymmetry into physics, pointing from ordered past toward disordered future. The second law is statistical rather than absolute. Microscopic physical laws are time reversible, but the vast majority of possible trajectories lead from lower to higher entropy simply because far more high entropy states exist than low entropy states. A box of gas molecules confined to one corner will spontaneously spread throughout the box because the overwhelmingly probable evolution is toward uniform distribution. Nothing prevents all molecules from randomly congregating back in the corner, but the probability is negligibly small, approximately 10 to the negative 10 to the 23rd for a mole of gas. The second law states that systems overwhelmingly evolve from improbable configurations toward probable ones. Entropy decreases are not impossible, merely preposterously unlikely for macroscopic systems. Entropy governs all irreversible processes we observe. When hot and cold objects contact, heat flows from hot to cold until temperatures equalize, increasing entropy. Mixing two gases produces a uniform mixture, increasing entropy. Breaking an egg scrambles its ordered structure, increasing entropy. Stars fuse lighter elements into heavier ones and radiate energy into space, increasing the universe's total entropy. Chemical reactions proceed in directions that increase overall entropy when coupled to surroundings. Life temporarily decreases local entropy by creating ordered structures, but only by increasing environmental entropy more through metabolic heat and waste products. The total entropy always increases. Black holes possess enormous entropy proportional to their event horizon surface area. A solar mass black hole contains entropy of approximately 10 to the 54th in Boltzmann constant units. A supermassive black hole with 1 billion solar masses holds entropy exceeding 10 to the 77th. When matter falls into black holes, the universe's total entropy increases dramatically. Jacob Bekenstein and Stephen Hawking established this black hole entropy through theoretical arguments combining quantum mechanics, general relativity, and thermodynamics. The enormous entropy suggests black holes contain vast information encoded holographically on their two-dimensional event horizons. This connection between gravity, thermodynamics, and information theory hints at deeper underlying principles linking these seemingly distinct domains. The universe's total entropy has increased from the Big Bang's low entropy initial state toward ever higher values. Current entropy is dominated by photons in the cosmic microwave background radiation, approximately 10 to the 88th in Boltzmann constant units. Visible matter contributes relatively little entropy compared to radiation. As the universe evolves, entropy production continues through stellar burning, black hole formation and growth, and eventual black hole evaporation. In the far future, after stars fade and black holes dominate, black hole entropy will exceed all other contributions. When black holes evaporate through Hawking radiation, entropy continues increasing as radiation disperses through expanding space. The ultimate fate is maximum entropy heat death, where all energy exists as uniform low-temperature radiation filling space. In this state, no temperature differences exist to drive processes. No work can be extracted, no structures can form or persist. The universe reaches perfect thermodynamic equilibrium at temperatures approaching absolute zero. Entropy has reached its maximum possible value. The second law permits no further increase because no higher entropy states exist. Time's arrow becomes meaningless because no changes occur to distinguish past from future. The universe exists in eternal, changeless equilibrium, having exhausted all possibilities for increasing entropy. This represents not annihilation, but eternal stagnation. Existence continues, but nothing happens. Whether entropy could ever decrease on cosmic scales remains speculative. Some cyclic cosmology models propose mechanisms for entropy to reset between cycles, though the details face severe theoretical challenges. Eternal inflation might produce pocket universes with arbitrarily low entropy, but these represent new isolated systems rather than reversals within our universe. Quantum fluctuations could spontaneously decrease entropy locally, but fluctuations large enough to significantly affect cosmic entropy are exponentially rare. Within standard cosmology, entropy increases monotonically from the Big Bang until heat death, with no reversal mechanisms. The universe marches inexorably from order toward disorder, from structure toward uniformity, from interesting complexity toward featureless simplicity, following the second law's statistical imperative across cosmic timescales. Heat death, the final equilibrium. Heat death represents the universe's thermodynamic endpoint, a state where entropy reaches maximum and all energy exists as uniform radiation at near absolute zero temperature distributed throughout expanding space. No temperature gradients remain to drive processes. No work can be extracted because everything sits at equilibrium. Stars have exhausted nuclear fuel and faded. Black holes have evaporated through Hawking radiation. Matter has decayed into fundamental particles and photons. All processes that can occur have occurred. The universe enters a final eternal state where nothing further happens. Not destruction, but stagnation. Existence persists, but experiences nothing, frozen in changeless equilibrium. The timeline to heat death stretches far beyond human comprehension. Star formation will continue for approximately 100 trillion years, exhausting available gas. The longest-lived stars, red dwarfs, with 1/10 the sun's mass burn hydrogen for trillions of years. The last stars will flicker out perhaps 120 trillion years from now, leaving behind cooling remnants. White dwarfs, neutron stars, and brown dwarfs will radiate away residual heat over 10 to the 20th years, approaching background temperature. Galaxies will evaporate as stars gravitationally scatter through near encounters, requiring 10 to the 19th to 10 to the 20th years. Remaining matter either falls into supermassive black holes at galactic centers or disperses into intergalactic space. Black holes dominate the intermediate era. After stars fade, black holes contain most organized energy, stellar mass black holes evaporate through Hawking radiation in approximately 10 to the 67th years. Supermassive black holes with billions of solar masses persist for 10 to the 100th years or longer. During this epoch, black hole evaporation represents the universe's only significant energy source. Though the emission is extraordinarily feeble, a solar mass black hole radiates mere billionths of a watt. As black holes shrink, Hawking temperature increases. They eventually explode in final bursts when reduced to microscopic sizes. After the last black holes evaporate around 10 to the 100th years, the universe contains only dilute radiation and fundamental particles. Proton decay, if it occurs, dismantles remaining matter. Grand unified theories predict protons decay with half-lives exceeding 10 to the 34th years, though experiments have not yet observed decay. If protons decay with half-lives around 10 to the 36th years, all matter composed of protons will disintegrate within 10 to the 40th years. Decay products include positrons, neutrinos, and photons. Electrons and positrons annihilate, producing gamma rays that redshift as space expands. Neutrinos stream freely through space, interacting negligibly. The universe transitions from containing atoms and matter to being a thin soup of radiation and possibly stable leptons, if electrons prove truly stable. Dark energy's influence strengthens as matter dilutes. Currently comprising 68% of total energy density, dark energy's fractional contribution approaches 100% as matter thins. If dark energy behaves as Einstein's cosmological constant with constant density, expansion continues, accelerating forever. The universe asymptotically approaches de Sitter space, exponentially expanding vacuum, with event horizons isolating finite regions. Each observer perceives only a limited bubble, approximately 16 billion light-years in radius. Beyond event horizons, regions permanently lose causal contact. The observable universe shrinks even as the total universe expands. In the heat-death state, temperature approaches but never quite reaches absolute zero. The cosmological constant provides a minimum temperature floor, approximately 10 to the negative 30th Kelvin, for measured dark energy density. This represents the Gibbons-Hawking temperature associated with de Sitter event horizons, analogous to Hawking radiation from black holes. At this temperature, thermal fluctuations have wavelengths exceeding cosmic horizons. The universe exists in a featureless thermal bath where nothing distinguishes one location from another, nor one moment from another. Quantum fluctuations, particles spontaneously appearing and vanishing, occur extremely rarely at such low temperatures, but represent the only events breaking perfect stasis. Heat death is not destruction, but eternal, unchanging existence. The universe persists forever in a state where time loses operational meaning. Without entropy gradients, no arrow of time exists. Without structure or change, no events mark temporal progression. Observers, if they could somehow exist, would experience nothing: no light, no heat, no detectable phenomena. The universe continues but experiences cessation. This represents reality's thermodynamic conclusion, not in annihilation, but in transformation to an eternal, featureless state where existence persists, but nothing interesting or complex can ever occur again across infinite future. Time, the big rip torn apart by expansion. Phantom dark energy, if it exists, would cause the universe to end in the big rip, a catastrophic scenario where accelerating expansion tears apart all structures, including space-time itself, within finite time. Phantom energy has an equation of state parameter W less than -1, meaning its density increases as the universe expands, rather than remaining constant like a cosmological constant. This creates runaway acceleration, where expansion rates grow exponentially, eventually overwhelming all forces: electromagnetic, nuclear, and even gravitational that hold structures together. Calculations predict that if W equals negative 1.5, the universe ends approximately 22 billion years from now in total disintegration. The progression toward the Big Rip follows a predictable sequence as phantom energy density increases and expansion accelerates to extreme rates. Approximately 60 million years before the Rip, galaxies unbind as phantom energy overcomes gravitational attraction, holding galaxy clusters together. Individual galaxies lose their surrounding gas, and satellite galaxies to accelerating expansion. The Virgo cluster, Coma cluster, and all large-scale structures dissolve as member galaxies scatter into expanding voids. 1 billion years before the end, galaxies themselves disintegrate as dark energy density locally overcomes galactic self-gravity. The Milky Way and Andromeda, currently approaching each other for eventual merger, would never collide. Instead, both scatter into isolated stars, drifting through expanding space. Approximately 3 months before the Big Rip, planetary systems unbind. Dark energy density surpasses local gravitational binding energy of star systems. Earth would be torn from solar orbit, flung into interstellar space along with all other planets, asteroids, and comets. The Sun becomes an isolated star, surrounded by expanding empty space as its retinue of planets disperses in all directions at increasing velocities. Jupiter, Saturn, and the outer planets would separate first, followed by the inner rocky worlds. The Moon would separate from Earth days later, as tidal forces from expansion overcome lunar orbital binding. 1 hour before the end, planets themselves disintegrate. Gravitational self-attraction can no longer hold planetary matter together against phantom energies accelerating expansion. Earth tears apart, its fragments separating at increasing velocities. In the final minutes, stars explode as phantom energy overcomes nuclear forces binding atomic nuclei. The Sun and all stars throughout the universe detonate not through fusion, but through expansion, literally tearing nuclear matter apart. Individual atoms disintegrate in the last 10 to the negative 19th seconds before the Rip. Electromagnetic forces can no longer bind electrons to nuclei against expansion's pull. Electrons separate from protons. Nuclei fragment into individual protons and neutrons. The familiar periodic table dissolves as atoms cease existing. Finally, at the singularity, space-time itself tears. The fabric of space develops infinite curvature. General relativity predicts a future singularity where physical laws cease functioning, analogous to the Big Bang singularity, but occurring everywhere simultaneously rather than at one point. Current observations constrain but do not eliminate phantom energy. Measurements indicate W equals approximately -1, with uncertainties of a few percent consistent with a cosmological constant, but also compatible with W slightly less than -1. If future precise measurements determine W equals -1.05, the Big Rip becomes inevitable, though occurring perhaps 100 billion years in the future rather than 22 billion. Even slight deviations from -1 have dramatic consequences, given exponential effects accumulating over cosmic time. The Vera Rubin Observatory, Euclid Space Telescope, and Nancy Grace Roman Space Telescope will measure W to sub% precision within the next decade, potentially revealing whether phantom energy threatens reality's violent termination. The Big Rip represents physics breaking down completely, rather than reaching a stable endpoint, like heat death. Heat death preserves physical laws. The universe just reaches maximum entropy equilibrium, where nothing interesting occurs. The Big Rip destroys the framework within which physics operates. When space-time tears, general relativity's equations encounter singularities where predictions become meaningless. Whether quantum gravity effects prevent the singularity, replacing it with a bounce or transition to different physics remains unknown. No theory adequately describes physics at the Big Rip singularity. String theory, loop quantum gravity, and other quantum gravity approaches might predict exotic outcomes, but current formulations cannot reliably model such extreme conditions. If phantom energy exists, we live during the universe's final chapter, the last era before violent disintegration. The current epoch happens to coincide with dark energy dominance beginning. Observable universe expansion is accelerating, but has not yet reached catastrophic rates. Structures remain bound by gravity. Atoms persist. Physics functions normally. But this represents a temporary lull before exponential acceleration tears everything apart. Future civilizations billions of years hence would observe galaxies scattering, expansion accelerating to alarming rates, and realize their universe approaches inevitable destruction. They would have no escape. No technology could prevent the rip. Reality would end not in whimper, but in complete annihilation within finite time, tearing everything matter, light, space-time itself, to shreds in the universe's most violent possible conclusion, the Big Crunch, collapsing universe. The Big Crunch represents an alternative ending where cosmic expansion reverses, causing all matter to fall back together into a final singularity. This scenario occurs if the universe contains sufficient matter density to overcome expansion through gravitational attraction. In standard cosmology, three possible geometries exist: open, flat, and closed. A closed universe with positive spatial curvature contains enough matter that expansion eventually halts and reverses. Current observations indicate the universe is flat or very nearly so, making a big crunch unlikely given measured matter and dark energy densities. However, if dark energy weakens or reverses sign in the distant future, contraction could still occur despite current expansion acceleration. The timeline of a big crunch mirrors expansion in reverse, but with crucial differences. As contraction begins, galaxies that were receding due to expansion start approaching. The cosmic microwave background radiation, currently at 2.725 Kelvin, blue shifts instead of red shifts, gradually increasing in temperature. Initially, contraction proceeds slowly over billions of years. Galaxy clusters merge as space between them shrinks. Intergalactic gas compresses and heats. As contraction accelerates, the night sky brightens as distant galaxies blue shift from infrared to visible to ultraviolet wavelengths. Eventually, the sky becomes uniformly luminous as cosmic background radiation temperature exceeds that of stars, flooding the universe with increasingly energetic photons. Approximately 100 million years before the crunch, the cosmic microwave background temperature exceeds stellar surface temperatures, thousands of Kelvin. Planets and asteroids heat up from external radiation rather than internal sources. Oceans boil away, atmospheres strip from rocky worlds. Life becomes impossible as surface temperatures climb beyond biological tolerance. Stars themselves heat from outside, their surfaces bathed in radiation hotter than their cores. Normal stellar structure inverts as external heating dominates. Photospheres evaporate. Stellar envelopes expand, then dissipate. The distinction between stars and their surroundings blurs as everything approaches thermal equilibrium at rising temperatures. 1 year before the crunch, temperature reaches millions of Kelvin. Stars disintegrate as thermal radiation ionizes all matter. Atomic nuclei separate from electrons. Molecules dissociate. Chemistry ceases as thermal energies exceed chemical binding energies. The universe becomes an opaque plasma, similar to conditions shortly after the Big Bang, but in reverse time order, progressing from structure toward simplicity, from complexity toward uniformity. Atoms that formed 380,000 years after the Big Bang, when the universe cooled below 3000 Kelvin, now dissociate as temperatures climb back above ionization thresholds. The universe retraces its evolutionary path, but with crucial thermodynamic differences. In the final minutes, nuclei themselves disintegrate as temperatures exceed billions of Kelvin energies sufficient for nuclear breakup. Protons and neutrons separate from larger nuclei. Deuterium, helium, carbon, oxygen, iron, all elements forged in stellar cores over billions of years, decompose back into individual nucleons. Matter reduces to a soup of protons, neutrons, and electrons swimming in intense radiation. In the last microseconds, even protons and neutrons dissolve into quarks and gluons as temperatures reach trillions of Kelvin and energies approach the quantum chromodynamic scale. The universe approaches Planck energy densities of 10 to the 19th billion electron volts, where quantum gravitational effects dominate and general relativity's predictions become unreliable. The crunch culminates in a singularity, all matter and energy compressed into zero volume at infinite density and temperature. General relativity predicts this singularity is unavoidable in a collapsing universe, though quantum gravity effects might intervene at Planck scales. At the singularity, space-time curvature becomes infinite. Physical laws as we know them cease functioning. Whether the singularity represents an absolute endpoint or a transition to something else remains unknown. Some models propose that quantum effects cause a bounce, initiating a new expansion cycle. Others suggest transitions to higher dimensional spaces or different vacuum states. Without a complete theory of quantum gravity, singularity physics remains speculative. The Big Crunch differs fundamentally from a time-reversed Big Bang, despite superficial similarities. Entropy continues increasing throughout contraction, violating time reversal symmetry. The crunch represents a high-entropy disordered state rather than the low-entropy ordered Big Bang beginning. Stellar collisions during galaxy mergers, radiation produced by compression heating, and black hole growth all increase entropy. The time asymmetry comes from thermodynamics, not gravity. Gravity itself is time-symmetric gravitational equations, work equally well for expansion or contraction. But thermodynamic processes distinguish collapse from expansion, ensuring the arrow of time points toward higher entropy, regardless of whether space expands or contracts. A big crunch does not lead naturally to a big bounce or new expansion cycle, because high entropy must somehow transition to low entropy for a bounce to initiate new expansion, requiring exotic physics or unknown mechanisms. Current observations strongly disfavor a big crunch. Measurements show dark energy causing accelerated expansion, not deceleration toward contraction. The universe appears spatially flat rather than closed with positive curvature. Extrapolating forward using measured parameters predicts eternal expansion leading to heat death, not eventual collapse. The universe's fate seems sealed endless expansion into cold emptiness rather than cataclysmic collapse. However, uncertainties remain about dark energy's long-term behavior spanning trillions of years. If dark energy decays or transitions to attractive gravity rather than repulsion, contraction could begin far in the future. While current data overwhelmingly favor eternal expansion, a big crunch remains possible if our understanding of dark energy proves incomplete or if presently unknown physics alters cosmic evolution on timescales exceeding current predictions. Vacuum decay reality phase transition. Vacuum decay represents an existential threat where the universe's vacuum state, empty space itself, transitions from a metastable false vacuum to a lower energy true vacuum, destroying everything in a bubble expanding at light speed. This scenario emerges from quantum field theory's treatment of vacuum energy. The vacuum is not empty, but filled with quantum fields whose ground states contribute to vacuum energy density. Our universe's vacuum might exist in a local minimum of its energy potential, a false vacuum stable against small perturbations, but capable of tunneling to a deeper true vacuum through quantum mechanical processes. Such a transition would be catastrophic, releasing enormous energy and changing fundamental constants and particle properties. The Higgs field provides a concrete example motivating vacuum decay scenarios. The Higgs field permeates space with a non-zero value, the vacuum expectation value of approximately 246 billion electron volts, giving elementary particles their masses through interactions with the field. Measurements from the Large Hadron Collider determined the Higgs boson mass at approximately 125 billion electron volts. Combined with top quark mass measurements around 173 billion electron volts, calculations suggest the Higgs potential might not have a global minimum at its current value. At field values far exceeding current levels, energies around 10 to the 10th billion electron volts, approaching the Planck scale, the potential might dip below the current vacuum state, indicating metastability. If true, our vacuum could decay to this lower state through quantum tunneling. Vacuum decay initiates through quantum tunneling. A bubble of true vacuum spontaneously appears through quantum fluctuations, despite the energy barrier separating false and true vacua. Inside the bubble, the Higgs field settles at its true vacuum value, possibly zero or a different non-zero value. Physical constants and particle properties differ from outside. The bubble wall separates two different vacua, releasing energy equal to the vacuum energy difference, potentially enormous, given the Higgs potential scale. This energy drives the bubble wall outward at light speed. Nothing can outrun the expanding bubble. No warning signals can reach regions before the wall arrives, because the wall travels at light's maximum velocity. Observers far from the nucleation point would have no indication anything was wrong until the instant the wall hit. Inside the bubble, physics operates under different rules determined by the true vacuum's properties. If the Higgs field settles at zero, the standard model Higgs mechanism fails. Particles that acquire mass through Higgs interactions, quarks, charged leptons, weak force bosons, would become massless or acquire different masses through alternative mechanisms. Electrons might become heavier, protons lighter, or quarks unstable against decay. Chemical bonds depending on precise electron masses and electromagnetic coupling strengths would break. Atoms as we know them might not exist. Nuclear binding energies would shift, potentially destabilizing all nuclei. Fundamental force strengths could change, altering fusion rates, decay lifetimes, and interaction cross-sections. Any structures, stars, planets, molecules, organisms formed in the false vacuum would disintegrate instantly upon the wall's arrival. The probability of vacuum decay can be estimated but not predicted precisely without knowing the full vacuum energy potential. Quantum tunneling rates depend exponentially on barrier heights and potential shapes. For barriers significantly exceeding thermal energies, tunneling rates are extraordinarily low. Vacuum could remain metastable for times vastly exceeding the universe's current age. Calculations suggest that if our vacuum is metastable, the mean decay time might exceed 10 to the 100th years or longer, though large uncertainties exist from imprecise knowledge of the Higgs potential at extreme energies. Observational limits constrain this. The universe has persisted 13.8 billion years without observed vacuum decay in our region, implying either absolute stability or decay rates low enough that transitions have not occurred within the observable universe during cosmic history. Cosmic expansion affects vacuum decay rates and consequences. In an expanding universe, even if vacuum decay nucleates, the bubble might not consume everything. If expansion velocity exceeds the bubble wall's approach velocity at sufficiently large distances, distant regions recede beyond causal contact before the bubble reaches them. For exponentially expanding de Sitter space, driven by cosmological constant, bubbles nucleating now would fail to consume most of the universe, because accelerating expansion carries distant regions beyond reach faster than the bubble expands. However, for regions within the current cosmic event horizon, approximately 16 billion light-years vacuum decay bubbles expanding at light speed would consume everything, destroying local reality, even if distant regions survive. Vacuum decay is unpreventable if metastability exists. No technology could stop it. Quantum tunneling occurs spontaneously at random, unpredictable times and locations governed by probabilistic quantum mechanics. Civilizations cannot shield against it or detect it approaching, because the bubble wall travels at light speed with no forerunner signals. The best hope is that vacuum is actually absolutely stable, not metastable. Precise measurements of Higgs mass, top quark mass, and standard model parameters will determine whether calculations truly indicate metastability or if uncertainties allow for absolute stability. Current data marginally favor metastability, but with large uncertainties from imprecise top quark mass measurements and theoretical calculations at extreme energies. Future collider experiments, probing higher energies, and theoretical refinements might clarify the situation. If vacuum is metastable, we exist in a temporary reality that could end without warning through a quantum fluctuation, transforming everything into unrecognizable physics, erasing the universe as we know it. Proton decay matter falls apart. Proton decay, if it occurs, represents the gradual dissolution of ordinary matter into lighter particles and radiation over incomprehensible timescales. The standard model of particle physics predicts stable protons, the nucleus of hydrogen atoms and constituents of all atomic nuclei, would persist forever without decaying. However, grand unified theories, abbreviated GUT, which attempt to unify electromagnetic, weak, and strong nuclear forces into a single framework at high energies, predict protons decay with finite lifetimes. In these theories, quarks can transform into leptons through interactions mediated by extremely massive hypothetical particles called X bosons and Y bosons, with masses around 10 to the 15th billion electron volts. Such transformations violate baryon number conservation, allowing protons to decay into lighter particles. Typical GUT decay modes convert a proton into a positron and a neutral pion, with the pion immediately decaying into gamma rays. The process begins when two quarks inside the proton exchange an X boson, converting one quark into an antiquark and a lepton. The resulting particles rearrange into observable decay products. Alternative decay modes produce different final states. Protons might decay into kaons and neutrinos, or into muons and pions. Each mode has different probabilities and slightly different predicted lifetimes, but all exceed 10 to the 30th years by enormous margins. Early GUT theories predicted proton lifetimes around 10 to the 31st years, but experiments quickly ruled out this range by observing large numbers of protons for extended periods without detecting decay. Experimental searches for proton decay use massive detectors containing thousands of tons of water or other materials, monitoring for characteristic decay signatures. Super Kamiokande in Japan contains 50,000 tons of ultra-pure water, surrounded by photomultiplier tubes, detecting light from particle interactions. If a proton decays, the positron and pion products produce distinctive light signatures that can be distinguished from background radiation and cosmic ray interactions. After decades of observation, no confirmed proton decays have been detected. These null results place stringent lower limits on proton lifetime, currently exceeding 10 to the 34th years for common decay modes. This enormous lifetime means that in a human body containing roughly 10 to the 28th protons, we would expect less than 1 proton decay per century, even at the experimental lower limit. If protons decay with lifetimes around 10 to the 36th years, within the range predicted by some supersymmetric gut models, all ordinary matter will disintegrate within approximately 10 to the 40th years. This timeline vastly exceeds stellar lifetimes, black hole evaporation times for stellar mass black holes, and even the era when galaxies evaporate. But it occurs before supermassive black holes evaporate, which require up to 10 to the 100th years. During the proton decay era, any remaining planets, asteroids, brown dwarfs, white dwarfs, and neutron stars, composed of protons and neutrons, would gradually disintegrate. Each proton decay converts nuclear matter into positrons, neutrinos, and photons. Positrons encounter electrons and annihilate, producing additional gamma rays that redshift as space expands. The decay products disperse through expanding space. Positrons and electrons annihilate within short times after proton decay, leaving only photons and neutrinos. Photons stretch to longer wavelengths as cosmic expansion continues. Neutrinos, produced copiously in proton decay, stream freely through space, interacting negligibly with anything. The universe transitions from containing structured matter atoms, nuclei, and complex materials formed over cosmic history to a diffuse bath of radiation and leptons. If electrons are absolutely stable, as the Standard Model suggests, free electrons persist indefinitely. But without protons to bind to, chemistry becomes impossible. Atoms cease existing. The universe becomes a thin soup of photons, neutrinos, and possibly electrons, continuing to expand and cool toward absolute zero. The question of whether protons actually decay remains open. No experiment has detected decay, only placed lower limits on lifetime. The Standard Model's prediction of absolute proton stability might be correct, in which case matter persists indefinitely in some form. Alternatively, proton decay might occur with lifetimes exceeding current experimental limits, perhaps 10 to the 40th years, or even 10 to the 100th years, making detection impossible with foreseeable technology. Future experiments will push limits higher by using larger detectors and longer observation times. The proposed Hyper Kamiokande detector, 8 times larger than Super Kamiokande, will improve sensitivity by detecting more potential decay events. Deep underground neutrino experiments like June might also contribute by detecting decay products. If protons never decay, matter in some form persists eternally, though distributed so thinly and at such low temperatures that complex structures cannot exist. Isolated electrons and protons drift through expanding space, separated by light years, never interacting. If protons decay, even this tenuous matter eventually vanishes, leaving only radiation and perhaps electrons. Either way, the familiar world of atoms, molecules, and solid matter has long since disappeared, dissolved by expansion, cooling, and potentially decay into an unrecognizably simple final state. Whether protons decay determines if reality retains any material substrate or becomes purely radiative. But the functional difference is minimal given the enormous timescales and extreme dilution. By the proton decay era, if it occurs, reality is already transformed beyond recognition into a cold, dark, nearly empty void. Black holes devour, then evaporate. Black holes represent the ultimate fate of massive stars and the final repositories for matter falling into galactic centers. These objects grow by accreting surrounding gas and by merging with other black holes during galaxy collisions. Over cosmic time, black holes steadily increase in mass, devouring stars that wander too close, capturing planets and asteroids, and feeding on interstellar gas. Supermassive black holes at galactic centers contain millions to billions of solar masses. Stellar mass black holes formed from individual stars range from a few to tens of solar masses. Intermediate mass black holes, if they exist, bridge the gap. All black holes, regardless of size, share a common fate. They eventually evaporate through Hawking radiation, a quantum mechanical process discovered theoretically by Stephen Hawking in 1974. Hawking radiation arises from quantum fluctuations near the event horizon. Throughout space, virtual particle-antiparticle pairs spontaneously appear from vacuum energy, typically annihilating each other almost immediately. Near a black hole's event horizon, one particle can fall into the black hole while its partner escapes to infinity. The escaping particle becomes real radiation, carrying away energy. This energy must come from somewhere. It is extracted from the black hole's mass energy. The black hole loses mass through this quantum mechanical emission process. The radiation appears thermal, characterized by a temperature inversely proportional to the black hole's mass. Larger black holes have lower Hawking temperatures, smaller black holes are hotter. For stellar mass and supermassive black holes, Hawking temperature is extraordinarily low, far below the cosmic microwave background temperature of 2.725 Kelvin. A solar mass black hole has a Hawking temperature of approximately 60 billionths of a Kelvin. A billion solar mass supermassive black hole has a temperature near 10 to the negative 14th Kelvin. At these temperatures, black holes currently absorb more energy from the cosmic microwave background than they emit through Hawking radiation. They grow rather than shrink. Only after the universe expands and cools sufficiently, when the background temperature redshifts below the Hawking temperature, do black holes begin net evaporation. This will occur trillions of years in the future, as cosmic expansion dilutes and cools the microwave background radiation. The evaporation timescale depends strongly on mass. Hawking's calculations show that evaporation time scales as mass cubed. A solar mass black hole requires approximately 10 to the 67th years to evaporate completely. A supermassive black hole with a billion solar masses persists for roughly 10 to the 100th years. These timescales dwarf all other cosmic timescales. The current age of the universe is merely 1.38 times 10 to the 10th years. Black holes will persist long after all stars have burned out, all planets have cooled, and even after protons have decayed if decay occurs. For most of the universe's far future, black holes represent the only significant concentrations of energy and mass in an otherwise empty expanding void. As black holes evaporate, they grow hotter. The temperature is inversely proportional to mass, so as mass decreases, temperature increases. A shrinking black hole radiates faster, losing mass at accelerating rates in a runaway process. Initially, evaporation proceeds imperceptibly slowly over timescales exceeding Google years. But in the final stages, evaporation accelerates dramatically. When reduced to asteroid mass around 10 to the 11th kilograms, the black hole has a Hawking temperature of approximately 100 million Kelvin and evaporates in days. At planetary mass, evaporation requires years. In its final second, a black hole releases energy equivalent to millions of nuclear weapons as it explosively evaporates, converting its remaining mass into a burst of particles and high-energy radiation. The evaporation endpoint remains uncertain. Classical general relativity predicts complete evaporation until nothing remains. However, quantum gravity effects might intervene at Planck mass scales, approximately 10 to the negative 8th kilograms, where quantum and gravitational effects become equally important. Some theories suggest evaporation halts at Planck mass, leaving stable remnants. These Planck mass black hole remnants would persist indefinitely, storing information about everything that fell into the original black hole. Alternative theories propose that evaporation continues until complete annihilation, with information somehow encoded in subtle correlations in the emitted radiation. The information paradox, whether information about infalling matter is destroyed or preserved, remains unsolved, hinging on details of quantum gravity that exceed current understanding. After the last black holes evaporate around 10 to the 100th years, the universe contains only radiation and possibly electrons, if they are stable. All the matter that fell into black holes over cosmic history, stars, planets, gas, dust, has been converted to Hawking radiation and dispersed through expanding space. The photons composing this radiation continue redshifting as expansion proceeds. The universe becomes an ever-thinning bath of extremely low-energy photons with wavelengths exceeding galaxies, neutrinos streaming freely, and possibly isolated electrons separated by incomprehensible distances. Black holes, which dominated the middle era of cosmic history, have vanished, completing their cycle from growth through accretion to dissolution through evaporation. Their disappearance marks the end of the last major energy sources in the universe, leaving only the slow drift toward heat death. Dark energy, mysterious acceleration. Dark energy, comprising approximately 68% of the universe's total energy density, drives cosmic expansion's acceleration, yet remains one of physics' deepest mysteries. This component was discovered in 1998 by two independent teams studying Type Ia supernovae, exploding white dwarf stars, used as standard candles to measure cosmic distances. The teams found that distant supernovae appeared dimmer than expected if expansion had been decelerating, as predicted by matter-dominated cosmology. The only explanation consistent with observations was accelerating expansion driven by a repulsive form of energy filling space. These observations revolutionized cosmology and earned Saul Perlmutter, Brian Schmidt, and Adam Riess the 2011 Nobel Prize in Physics. The simplest dark energy model treats it as Einstein's cosmological constant lambda, a constant energy density inherent to empty space itself. Einstein introduced the cosmological constant in 1917 as an additional term in general relativity's field equations, seeking to create a static universe by balancing gravitational attraction with cosmic repulsion. He later abandoned this after Hubble discovered cosmic expansion, reportedly calling it his greatest blunder. The cosmological constant can be interpreted as vacuum energy, energy intrinsic to space arising from quantum field fluctuations. Quantum field theory predicts vacuum contains zero-point energy from virtual particles constantly appearing and disappearing. This vacuum energy acts as a cosmological constant, producing gravitational repulsion that drives accelerated expansion. However, quantum field theory faces a catastrophic prediction problem. Naive calculations of vacuum energy density from quantum fluctuations yield values approximately 10 to the 120th times larger than the observed dark energy density. This represents the worst theoretical prediction in physics history, off by 120 orders of magnitude. Somehow, the enormous vacuum energy contributions from quantum fields must cancel to incredible precision, leaving only the tiny observed value. This fine-tuning problem remains unexplained. Various theoretical approaches, supersymmetry, extra dimensions, anthropic selection in a multiverse attempt to explain the observed value, but without definitive success. The cosmological constant problem ranks among the most profound unsolved puzzles in theoretical physics. Current observations constrain dark energy's properties through the equation of state parameter W, defined as pressure divided by energy density. A cosmological constant has W equal to precisely -1 pressure, is negative, and exactly equals negative energy density. Negative pressure creates gravitational repulsion, driving accelerated expansion. Measurements from supernova surveys, cosmic microwave background observations, and baryon acoustic oscillations patterns in galaxy clustering constrain W to approximately -1 with uncertainties of a few percent. These measurements are consistent with a cosmological constant, but do not definitively prove dark energy has constant density. The parameter W might vary with cosmic time or differ slightly from -1. Quintessence models propose dark energy as a dynamical scalar field with evolving density and pressure. Unlike the cosmological constant's fixed density, quintessence energy density decreases as the universe expands, though more slowly than matter or radiation densities. The quintessence field slowly rolls down its potential energy curve, with the field's value determining energy density. Various quintessence models predict different evolution histories and equation of state parameters varying with time. Tracker quintessence fields naturally approach densities comparable to matter density regardless of initial conditions, potentially addressing the cosmic coincidence problem, why dark energy and matter densities are similar now, despite evolving differently. Distinguishing quintessence from a cosmological constant requires measuring how W changes over cosmic time through observations spanning billions of years of cosmic history. Phantom energy represents an even more exotic possibility with W less than -1. Phantom energy density increases as the universe expands rather than remaining constant or decreasing. This violates the weak energy condition, a theoretical requirement that energy density plus pressure remains non-negative. Phantom energy drives exponentially accelerating expansion that eventually tears apart all gravitationally bound structures in the Big Rip scenario. Current observations marginally favor W slightly greater than -1, suggesting phantom energy is unlikely, but uncertainties remain large enough that phantom energy cannot be definitively ruled out. Future observations will tighten constraints, potentially revealing whether phantom energy threatens the universe with violent disintegration. The future of dark energy research depends on ambitious surveys measuring cosmic expansion history with unprecedented precision. The Dark Energy Spectroscopic Instrument, abbreviated DESI, measures spectra of 30 million galaxies and quasars to map three-dimensional cosmic structure and determine expansion history across billions of years. The Vera Rubin Observatory will discover and monitor thousands of supernovae, providing distance measurements spanning cosmic time. The Euclid Space Telescope measures galaxy shapes and distributions to constrain dark energy through gravitational lensing effects and galaxy clustering. The Nancy Grace Roman Space Telescope combines supernova observations with weak lensing to measure dark energy parameters. Together, these surveys will constrain W to sub% precision and determine if it varies with time, potentially revealing dark energy's fundamental nature or demanding new physics beyond current cosmological frameworks. False vacuum metastability. The universe's vacuum state might exist in a metastable configuration, a false vacuum that appears stable but could decay to a lower energy, true vacuum through quantum tunneling. This scenario arises from quantum field theory's treatment of field potentials. Fields like the Higgs field have potential energy functions determining their ground states. The true ground state corresponds to the potential's global minimum, but potentials might have multiple local minima valleys separated by energy barriers. A field trapped in a local minimum exists in a false vacuum, stable against small perturbations but capable of tunneling through the barrier to the global minimum. Such a transition would be catastrophic, fundamentally altering physics throughout the affected region. The Higgs field exemplifies this concern. The Higgs potential's shape depends on the Higgs boson mass and top quark mass, both measured experimentally. With a Higgs mass of approximately 125 billion electron volts and top quark mass around 173 billion electron volts, calculations suggest the Higgs potential might develop a second, deeper minimum at field values far exceeding the current vacuum expectation value. If this calculation is correct, our vacuum exists in a local minimum, while a true vacuum with different Higgs field value represents the global minimum. The barrier separating these states prevents immediate decay, but quantum tunneling makes decay inevitable given sufficient time. The question is not if, but when. Vacuum stability calculations depend sensitively on precise measurements of particle masses and coupling constants. The top quark mass is particularly crucial. Heavier top quarks favor instability, while lighter masses favor absolute stability. Current measurements place the top quark mass in a region where calculations suggest metastability. The vacuum is not absolutely stable, but also not imminently unstable. The uncertainty in top quark mass measurements, roughly plus or minus 1 billion electron volts, translates to significant uncertainty in stability conclusions. Improved measurements from future colliders, like the proposed International Linear Collider or Future Circular Collider, will reduce these uncertainties, potentially determining definitively whether our vacuum is absolutely stable or merely metastable. If the vacuum is metastable, quantum tunneling will eventually nucleate a true vacuum bubble. The tunneling probability per unit volume per unit time can be estimated from the barrier height and potential shape, but large theoretical uncertainties exist. Calculations suggest vacuum decay rates might be incredibly low mean decay times, perhaps exceeding 10 to the 500th years, far longer than any other timescale in the universe. The observable universe, with volume around 10 to the 80th cubic meters and age 10 to the 17th seconds, has provided 10 to the 97th cubic meter seconds of opportunity for vacuum decay. The absence of observed decay constrains the decay rate but cannot rule out metastability with extremely long mean lifetimes. Cosmic inflation affects vacuum stability calculations. During inflation, the Higgs field experienced quantum fluctuations that might have driven it to large values, where the potential becomes unstable. If the Higgs field reached unstable regions during inflation, the universe should have undergone catastrophic vacuum decay, which obviously did not occur. This provides additional constraints on vacuum stability. Either the vacuum is absolutely stable, or inflation's details somehow prevented the Higgs field from reaching dangerous values, or the effective Higgs potential during inflation differed from current calculations. Understanding this tension requires better knowledge of both inflation dynamics and Higgs physics at extreme energies. Modified gravity or new physics beyond the standard model might alter stability conclusions. If additional fields or interactions exist at high energies, they could stabilize the Higgs potential, converting apparent metastability into absolute stability. Supersymmetry, if realized in nature, introduces additional particles that modify Higgs potential calculations. Extra dimensions, string theory constructions, or other beyond standard model physics might ensure stability through mechanisms not present in current calculations. Alternatively, multiverse scenarios might invoke anthropic selection. We observe a metastable vacuum because stable vacua do not permit complex structure and life, while only metastable vacua allow for sufficient richness to produce observers before inevitable decay. The implications of metastability are profound. If our vacuum can decay, then reality, as we know it, exists on borrowed time. No warning would precede the end. A bubble of true vacuum could nucleate anywhere in the universe at any moment, expanding at light speed and transforming physics. Everything inside the bubble would be destroyed or fundamentally altered beyond recognition. We could never see it coming because the bubble wall travels at light speed. Our existence depends on quantum mechanical probabilities, the dice rolls that determine when and where tunneling occurs. While the odds might favor stability for timescales far exceeding the universe's current age, the uncertainty remains unsettling. We might inhabit a temporary universe destined for inevitable transformation when quantum fluctuations finally trigger the transition to true vacuum. The cosmic microwave background fading evidence. The cosmic microwave background radiation, abbreviated CMB, represents the oldest light in the universe. Photons released 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before this recombination epoch, the universe was opaque. Free electrons scattered photons continuously, preventing light from traveling far. After recombination, photons decoupled from matter and streamed freely through space. These photons, initially emitted as visible and ultraviolet light from the 3000 Kelvin plasma, have been traveling for 13.8 billion years. Cosmic expansion stretched their wavelengths, redshifting them to microwave frequencies. Today, the CMB appears as nearly uniform radiation at 2.725 Kelvin, coming from all directions in the sky. The CMB provides crucial evidence for the Big Bang and cosmic evolution. Its near-perfect blackbody spectrum matches theoretical predictions with extraordinary precision. Tiny temperature fluctuations, variations of about 1 part in 100,000, reveal density variations in the early universe that seeded galaxy formation. Satellites like COBE, WMAP, and Planck mapped these fluctuations with increasing precision, determining cosmic parameters, including the universe's age, geometry, and composition. The CMB's properties confirm inflation theory, support dark matter and dark energy models, and validate the hot Big Bang framework. Without the CMB, much of modern cosmology would lack empirical foundation. However, the CMB is gradually fading due to cosmic expansion. As space expands, CMB photons redshift to longer wavelengths and lower energies. The temperature decreases inversely proportional to the universe's scale factor. When the universe doubles in size, CMB temperature halves. Currently at 2.725 Kelvin, the CMB will cool to 1 Kelvin in approximately 15 billion years, to 0.1 Kelvin in 150 billion years, and asymptotically approach absolute zero as expansion continues. The photons themselves persist, but their wavelengths stretch to meters, kilometers, and eventually light years. Detecting such long wavelength radiation becomes impossible with any conceivable technology. The CMB will effectively disappear from observability. The timeline of CMB fade-out has profound implications for future cosmology. Within a few 100 billion years, the CMB temperature will fall below 0.01 Kelvin, with wavelengths exceeding kilometers. Radio telescopes capable of detecting such long wavelengths would need to be larger than planets, making observation impractical. The CMB, which currently provides a uniform background at microwave frequencies detectable by small antennas, will have redshifted into unobservable territory. Future civilizations arising trillions of years from now will have no access to this crucial evidence. They cannot observe the CMB's blackbody spectrum, cannot map its temperature fluctuations, cannot confirm its properties. Without CMB observations, future cosmologists would struggle to reconstruct cosmic history. The Big Bang theory relies heavily on CMB evidence, its existence, temperature, spectrum, and fluctuation patterns. Alternative theories that do not predict a CMB would be harder to rule out without this evidence. Steady-state cosmology, which posits no Big Bang and continuous matter creation, was definitively ruled out by the CMB's discovery in 1965. But in the far future, without CMB access, discriminating between different cosmological models becomes more difficult. Theoretical reasoning and local observations might still point toward Big Bang cosmology, but the direct empirical evidence will have vanished. The disappearance of galaxies beyond the event horizon compounds this problem. As discussed earlier, accelerating expansion will eventually place all galaxies, except those in the local group, beyond observability. Future observers will see only one merged galaxy, surrounded by darkness, with no CMB and no external galaxies. Evidence for the Big Bang, cosmic expansion, the early universe's hot, dense state, and the existence of billions of galaxies will all have disappeared. Future cosmologists will inherit an impoverished universe, where the rich observational evidence available to us has been erased by expansion. They might deduce the truth through extraordinary theoretical insight, but they will lack confirmation. This raises disturbing epistemological questions. If critical evidence for cosmic history disappears over time, what evidence available to previous observers has already vanished that we cannot access? The universe might have passed through earlier phases, leaving evidence that has redshifted beyond detection or scattered beyond recovery. Our cosmological understanding might be incomplete, not because we lack intelligence or technology, but because we exist too late to observe certain phenomena. Conversely, we are fortunate to exist when crucial evidence remains accessible. The CMB is observable now because we live relatively early in cosmic history, before expansion has redshifted it to undetectable wavelengths. The fading CMB illustrates a general principle: observational reality changes with cosmic epoch. Earlier observers had access to different data than we do. Future observers will have less data than currently available. The universe's properties, expansion rate, temperature, visible structures evolve over time, changing what can be observed and measured. Scientific knowledge is contingent on when and where observers exist. This does not invalidate science, but emphasizes that our empirical foundation depends on fortunate cosmic timing. We observe the universe during a special epoch when rich evidence for its history and structure remains accessible. Future observers will not have this advantage, facing a darker, emptier, colder cosmos that has erased its own past. The CMB's fade-out represents not just losing a data source, but losing physical evidence that reality had a beginning, evolved through specific stages, and possesses properties extending far beyond what local observations reveal. Boltzmann brains and spontaneous observers. Boltzmann brains represent one of physics' most unsettling paradoxes: the possibility that random thermal fluctuations could spontaneously assemble conscious observers from thermal equilibrium conditions, and that such random observers might vastly outnumber evolved observers like humans. The concept originated with Ludwig Boltzmann's work on statistical mechanics in the late 1800s. Boltzmann realized that in a system at thermal equilibrium, maximum entropy random fluctuations constantly occur. While most fluctuations are small, extremely rare fluctuations could assemble complex ordered structures. Given infinite time, even extraordinarily improbable configurations would eventually occur, including configurations resembling conscious brains complete with false memories. The mathematical reasoning proceeds from statistical mechanics' foundation. At thermal equilibrium, the probability of finding a system in a particular microstate depends exponentially on that microstate's entropy. Higher entropy states are exponentially more probable than lower entropy states. A small fluctuation decreasing entropy slightly is relatively probable and occurs frequently. A large fluctuation creating a highly ordered structure is extraordinarily improbable, but not impossible. The probability falls exponentially with the magnitude of entropy decrease. For structures as complex as brains containing approximately 10 to the 26th atoms in precise organized arrangements, the fluctuation probability is negligibly small. But in infinite time at equilibrium, even such improbable events occur infinitely often. The Boltzmann brain problem emerges when considering the universe's far future. If the universe reaches heat-death thermal equilibrium and persists in that state forever, random fluctuations will eventually create every possible structure. Simple structures like atoms or molecules form relatively frequently through small fluctuations. Complex structures like stars, planets, or organisms require much larger fluctuations and are correspondingly rarer. But the rarest large fluctuations that create conscious observers would assemble minimal structures sufficient for consciousness, essentially free-floating brains with false memories of coherent lives. Such Boltzmann brains are vastly more probable than fluctuations, creating entire evolutionary histories leading to observers. This creates a disturbing implication. If the universe exists at thermal equilibrium for infinite time, the number of Boltzmann brains created by random fluctuations would vastly exceed the number of observers that evolved through normal cosmological and biological processes. Evolved observers like humans exist during the brief era between the Big Bang and heat death, when entropy is climbing and structure is possible. But this era is finite, perhaps 10 to the 100th years at most. The heat death era lasts forever. Infinite time at equilibrium produces infinite Boltzmann brains. The ratio of Boltzmann brains to evolved observers approaches infinity. If we assume we are typical observers, we should expect to be Boltzmann brains rather than evolved observers. But we do not observe ourselves to be Boltzmann brains. We possess coherent memories stretching back years, consistent with actual experienced histories rather than random false memories. Our observations match the predictions of physics and cosmology, suggesting real rather than illusory pasts. The photographs we see, records we read, and memories we share with others all cohere into consistent narratives. This suggests we are genuine, evolved observers. But if Boltzmann brains vastly outnumber evolved observers, our existence as evolved observers is statistically puzzling. The paradox challenges our understanding of probability, observation, and cosmology. Several resolutions have been proposed. One suggests the universe does not actually reach eternal thermal equilibrium. Perhaps cosmic evolution includes mechanisms that prevent heat-death phase transitions, vacuum decay, quantum processes, or unknown physics that disrupts equilibrium before infinite time elapses. If the equilibrium era is finite rather than infinite, Boltzmann brain production might remain small compared to evolved observers. Another resolution invokes observer selection effects. We necessarily observe ourselves as evolved observers because Boltzmann brains with random false memories would almost certainly not observe coherent physics or make self-consistent observations. Only evolved observers in real universes can do science and discover the Boltzmann brain problem. The anthropic principle plays a role in some resolutions. We observe this universe because its properties permit our existence. Universes or cosmic epochs that produce only Boltzmann brains would not support sustained observation, coherent reasoning, or the development of physics. By existing and asking questions, we demonstrate we are not typical random fluctuations, but members of the special class of observers embedded in structured, low-entropy environments. The measure over observers might weight evolved observers more heavily than Boltzmann brains, despite the numerical advantage. Perhaps because evolved observers persist longer, produce more observations, or participate more fully in the structure of reality. Alternatively, the Boltzmann brain problem might indicate an error in our cosmological models. If our physics predicts overwhelmingly probable Boltzmann brain dominance while we observe ourselves as evolved observers, perhaps our models are wrong. Heat death might not actually occur as predicted. The universe might be cyclic, with low entropy conditions recurring rather than settling into eternal equilibrium. Quantum cosmology might permit tunneling from equilibrium to new low entropy states, continually restarting structure formation. The problem might point toward new physics that prevents eternal equilibrium states. The Boltzmann brain paradox illustrates deep tensions between thermodynamics, cosmology, and probability theory applied to observers. It challenges our understanding of typicality, observation, and what it means to exist in a physical universe. If our cosmology predicts that most observers are random fluctuations, while we observe ourselves as evolved beings in a coherent universe, something in our framework must be revised. Whether the solution lies in better cosmology, refined probability measures, anthropic reasoning, or new physics remains debated. The paradox serves as a reminder that our understanding of reality's ultimate fate remains incomplete. The question of whether Boltzmann brains dominate the far future connects intimately to whether reality runs out in a particular way or continues evolving through mechanisms we have not yet discovered. The anthropic principle and observer selection. The anthropic principle recognizes that our observations of the universe are constrained by the requirement that conditions must permit our existence. This seemingly trivial observation has profound implications for understanding cosmic properties, fundamental constants, and reality's structure. The principle comes in two versions. The weak anthropic principle states that we necessarily observe a universe compatible with our existence. We could not observe a universe incapable of producing observers. The strong anthropic principle suggests the universe must have properties permitting observers to exist, implying teleology or design. Most physicists accept the weak version as a selection effect, while remaining skeptical of the strong version's teleological implications. The weak anthropic principle explains apparent fine-tuning in physical constants and cosmic conditions. Many fundamental parameters appear exquisitely tuned to permit life. The cosmological constant's value is approximately 10 to the 120th times smaller than naive quantum field theory predictions. Yet if it were much larger, galaxies could not form. The strong nuclear force strength determines whether stars can synthesize heavy elements. Slightly different values would prevent carbon or oxygen formation, precluding chemistry-based life. The electromagnetic force strength determines atomic properties, and chemical bonding different values might prevent stable atoms or molecules. The universe's dimensionality, expansion rate, matter-antimatter asymmetry, and numerous other properties appear fortuitously arranged to permit structure, complexity, and ultimately life. Traditional explanations for fine-tuning invoke design or necessity. Design arguments suggest an intelligent designer selected parameter values to permit life, a cosmological version of the argument from design for God's existence. Necessity arguments suggest parameters are determined by deeper principles. We have not yet discovered a final theory might predict observed values inevitably rather than contingently. But the anthropic principle offers an alternative. If many universes exist with different parameter values, we necessarily observe one compatible with our existence, regardless of how improbable such universes are. We cannot observe uninhabitable universes, creating an observation selection effect that explains apparent fine-tuning without invoking design or necessity. This reasoning requires a multiverse, multiple universes, with varying properties. Several frameworks provide such multiverses. Eternal inflation produces countless pocket universes with different vacuum states, potentially yielding different effective laws and constants in each pocket. String theory's landscape contains approximately 10 to the 500th possible vacuum configurations, each corresponding to a universe with different properties. Quantum many-worlds interpretation creates branching universes exploring all quantum possibilities. Each framework generates vast collections of universes with diverse properties. If we exist in a multiverse where different regions sample different physical laws, anthropic selection explains why we observe parameters compatible with life. Those are the only parameters observers can measure. The anthropic principle affects predictions about cosmic fate. If reality is structured such that only universes permitting observers exist or dominate the measure, then heat-death scenarios where observation becomes impossible might be disfavored. Perhaps mechanisms exist that prevent eternal equilibrium, maintain structure, or cycle through low entropy states, specifically because observer-permitting conditions are selected from among possible cosmic evolutions. This reasoning remains controversial. Critics argue it lacks predictive power and risks tautology. But some physicists take it seriously as a constraint on cosmological models, suggesting that eternal observer-hostile conditions might be less likely or less relevant than they appear. Anthropic reasoning faces serious challenges. It struggles with probability measures over infinite ensembles. How do we count universes or observers in an infinite multiverse to calculate probabilities? Different measures yield different predictions, and selecting measures seems arbitrary. The reasoning risks explaining everything while predicting nothing. Any observation can be anthropically explained as necessary for observers, making the principle unfalsifiable. Critics argue this violates scientific methodology, which demands testable predictions distinguishing theories. Anthropic explanations might be last resorts when no better explanation exists, not primary theoretical tools. Despite controversies, the anthropic principle highlights an important fact. Observer existence constrains possible observations. We cannot observe conditions incompatible with observers, creating selection bias in our data. This affects how we interpret measurements and predictions. For example, if vacuum decay could destroy the universe, anthropic reasoning explains why we observe a metastable vacuum that has not yet decayed. Universes where decay occurred early would not contain observers. If proton lifetimes were much shorter, matter would disintegrate before stars and planets formed, precluding complex chemistry and life. We necessarily observe proton lifetimes exceeding thresholds required for our existence. The anthropic principle's application to reality ending suggests that observer-hostile scenarios might be incomplete descriptions. If reality is fundamentally structured to permit observation, then complete heat death, Big Rip annihilation, or eternal equilibrium might not represent reality's final state. Instead, transitions to new phases, cyclic evolution, or unknown processes might maintain observer-permitting conditions. This does not guarantee immortality or comfort. Local regions might still face catastrophic endings, but it suggests the totality of reality might be more hospitable to observers than extrapolating current physics implies. Whether this reasoning is wishful thinking or deep insight remains debated, but it illustrates that observer existence is not incidental to physical cosmology. It constrains and informs our understanding of reality's structure and evolution. Cyclic cosmology, eternal recurrence. Cyclic cosmology proposes that the universe undergoes infinite cycles of expansion and contraction, or other forms of periodic behavior, with each cycle lasting tens or hundreds of billions of years, followed by a transition to the next cycle. This contrasts with standard Big Bang cosmology, predicting a single cycle starting with the Big Bang and ending in heat death, Big Rip, or Big Crunch. Cyclic models offer potential solutions to problems in standard cosmology, including the singularity problem, horizon problem, and flatness problem. They also provide a different answer to whether reality runs out. In cyclic cosmology, reality never ends, but renews itself eternally through successive cycles. The ekpyrotic model, derived from string theory, proposes that our universe exists on a three-dimensional brane, a membrane-like structure in a higher dimensional space. Parallel branes exist in this higher dimensional space, and their collisions create what we observe as Big Bangs. Before each collision, the branes slowly approach each other through a contracting phase that smooths out irregularities, explaining the universe's observed uniformity. When branes collide, enormous energy releases into our three-dimensional space, heating matter and radiation to extreme temperatures and initiating an expanding phase resembling the conventional Big Bang. After trillions of years of expansion, the brains separate and slowly approach again, beginning the next cycle. Conformal cyclic cosmology, proposed by Roger Penrose, takes a different approach based on conformal geometry. Penrose observes that the far future universe approaching heat-death cold, empty, dominated by massless radiation, becomes similar to the Big Bang's early state when viewed through conformal rescaling. In conformal geometry, distances and timescales can be rescaled without changing physics' essential features if only massless fields are present. Penrose proposes that the infinite future of one aeon becomes mathematically equivalent to the Big Bang beginning of the next aeon through conformal mapping. Each cycle lasts perhaps a googol years, fading into heat death that transitions into a new Big Bang, beginning the subsequent aeon. Loop quantum cosmology, derived from loop quantum gravity's attempt to quantize space-time, suggests that quantum effects replace classical singularities with bounces. In this framework, when the universe contracts toward what would classically be a Big Crunch singularity, quantum gravitational effects create enormous repulsion, preventing the singularity. Instead, the universe bounces into a new expanding phase. Similarly, the Big Bang singularity is replaced by a bounce from a previous contracting phase. The universe oscillates between expansions and contractions, with each bounce connecting cycles. The quantum bounce mechanism prevents infinite densities and temperatures, allowing physical laws to operate throughout, including at transitions. Cyclic models face significant challenges. Entropy poses a major problem. The second law of thermodynamics requires entropy to increase each cycle. If entropy increases monotonically across cycles, early cycles had lower entropy than later ones. Extrapolating backward, the first cycle must have had zero or minimal entropy. This reintroduces the fine-tuning problem cyclic models claim to solve. Why did the first cycle begin with special, low-entropy initial conditions? Alternatively, if cycles continue infinitely into the past, entropy becomes infinite, potentially making meaningful physics impossible. Some models propose mechanisms that reset or decrease entropy during transitions, but these mechanisms remain speculative and face theoretical difficulties. Observational tests might distinguish cyclic from single-cycle cosmologies. The cosmic microwave background radiation could contain signatures of previous cycles, anomalous patterns, or correlations not predicted by standard inflation. Gravitational wave backgrounds might carry information about bounces or brane collisions. Conformal cyclic cosmology predicts specific signatures called Hawking, points circular patterns in the CMB from supermassive black holes in the previous aeon. Searches for such patterns have reported tentative detections, though these remain controversial and require confirmation. Future observations with improved CMB measurements and gravitational wave detectors might provide definitive tests. If cyclic cosmology is correct, reality never truly runs out but continually renews itself. Each cycle might last tens or hundreds of billions of years, approaching heat death before transitioning to a new cycle. Observers in each cycle would perceive linear cosmic history, a Big Bang beginning, stellar era, possible dark age, and eventual ending. But from a multi-cycle perspective, this represents one episode in an infinite sequence. Previous cycles with their own galaxies, stars, and potentially civilizations preceded ours. Future cycles will follow after our universe fades or contracts. Reality is eternal in both temporal directions, with cycles extending infinitely into past and future. However, individual cycles still have beginnings and endings. If we exist in one cycle, our universe will eventually end through heat death, Big Crunch, or whatever transition mechanism leads to the next cycle. The transition might be catastrophic, destroying all structure and information from the previous cycle, or gentle preserving some information across cycles. Either way, the current cycle terminates, taking everything in it all: galaxies, stars, planets, civilizations, histories, into transformation. From our perspective, embedded in this cycle, reality does run out, even if the broader cyclic framework continues. The cyclic model provides comfort at a cosmic level by ensuring reality persists eternally, but offers little solace to beings within individual cycles facing their cycle's termination. Quantum fluctuations and instability. Quantum fluctuations permeate space at all scales, creating temporary violations of energy conservation through the uncertainty principle and generating virtual particles that spontaneously appear and disappear on timescales too brief to detect directly. These fluctuations are not mere theoretical constructs, but have observable consequences. The Casimir effect, Lamb shift, and Hawking radiation all arise from quantum vacuum fluctuations. While normally harmless, such fluctuations raise unsettling possibilities. Could quantum fluctuations nucleate catastrophic events like vacuum decay? Could they spontaneously create structures like Boltzmann brains, disembodied consciousnesses arising from random particle arrangements? Could reality itself be unstable at the quantum level? The uncertainty principle permits temporary energy violations. The product of energy uncertainty and time uncertainty must exceed Planck's constant divided by 4 pi. This allows particles with energy E to exist for times approximately equal to Planck's constant divided by 4 pi e. Higher energy violations persist for shorter times. Virtual particle pairs electrons and positrons. Quarks and antiquarks constantly pop in and out of existence throughout space. Most annihilate almost instantly. But near black hole event horizons, one particle can fall in while its partner escapes, creating Hawking radiation. Similar processes might occur elsewhere, virtual particles becoming real through interactions with fields or curved spacetime. Quantum tunneling allows systems to transition between states separated by energy barriers despite lacking sufficient energy to classically surmount the barrier. Particles tunnel through barriers by temporarily violating energy conservation, traversing distances they classically could not reach. This process, well established through countless experiments and applications from tunnel diodes to scanning tunneling microscopes, permits vacuum decay. The universe's vacuum state can tunnel from a metastable false vacuum to a stable true vacuum, even without sufficient energy to classically overcome the barrier. The tunneling probability depends exponentially on the barrier's height and width higher. Wider barriers are harder to tunnel through, resulting in longer mean tunneling times. Quantum fluctuations can spontaneously create complex structures given sufficient time and space. In an infinite universe, or given infinite time, even extremely improbable configurations will occur through random fluctuations. A particularly disturbing possibility is Boltzmann brains, disembodied consciousnesses arising from random particle arrangement. In a heat-death universe at thermal equilibrium, quantum fluctuations occasionally create ordered structures from the featureless background. Most fluctuations produce simple patterns, but extremely rare fluctuations could assemble particles into functional brains complete with memories and consciousness. Such Boltzmann brains would vastly outnumber evolved observers like humans in the far future heat-death era. The Boltzmann brain problem challenges our understanding of probability and observation. If most conscious observers in the universe's history are Boltzmann brains arising from random fluctuations rather than evolved beings, we should expect to be Boltzmann brains. But Boltzmann brains form with random false memories rather than coherent histories. Our observations appear consistent with real histories, suggesting we are not Boltzmann brains, This creates a paradox. Either the universe does not reach heat-death equilibrium where Boltzmann brains dominate, or our probability reasoning is flawed, or observers like us are indeed rare compared to Boltzmann brains, but the anthropic principle prevents us from observing as Boltzmann brains. The paradox motivates cosmological models that avoid eternal heat death. Quantum fluctuations might trigger cosmic catastrophes. Vacuum decay nucleation is essentially a quantum fluctuation. A bubble of true vacuum spontaneously appears through tunneling despite the energy barrier. Other possibilities include spontaneous black hole formation from quantum fluctuations if space becomes sufficiently curved, or fluctuations triggering inflation in local regions if vacuum energy conditions are met. While these events are extraordinarily improbable in normal spacetime, they illustrate that quantum mechanics introduces fundamental unpredictability and instability. Even seemingly stable configurations can spontaneously transition to radically different states through quantum processes. The measurement problem in quantum mechanics adds another layer of uncertainty to reality's stability. Quantum systems exist in superpositions of multiple states until observed, at which point wave functions collapse to definite states. What constitutes a measurement and what causes collapse remains debated. If consciousness is required for collapse, as some interpretations suggest, reality's structure depends on observers. In observer-free regions, systems might remain in superposition indefinitely. If observation defines reality, then regions beyond cosmic horizons, where observation is impossible, might exist in fundamentally different states or not exist in any definite state at all. The role of quantum mechanics in defining reality's structure and stability remains one of physics' deepest unsolved problems. The many worlds interpretation suggests quantum fluctuations do not represent instability, but rather branching into multiple realities. Every quantum event spawns multiple branches of the wave function, each representing a different outcome. Vacuum decay occurs in some branches, but not others. Boltzmann brains form in some branches, while evolved observers dominate others. We observe the branch consistent with our experiences. In this view, quantum mechanics does not threaten reality, but multiplies it, creating an ever-expanding tree of parallel universes encompassing all quantum possibilities. Reality does not run out, but proliferates endlessly through quantum branching. Though individual branches might end through various catastrophic scenarios, while other branches persist. Simulation hypothesis, programmed reality. The simulation hypothesis proposes that our reality is not fundamental, but rather a computational simulation run by advanced civilizations or entities with access to enormous computing resources. This idea, while seemingly far-fetched, gains plausibility from several considerations. First, computational power grows exponentially. Today's smartphones exceed the computing power of 1960s supercomputers. Extrapolating this trend suggests future civilizations might possess computing capabilities capable of simulating entire universes down to quantum levels. Second, if such simulations are possible, advanced civilizations might run many simulations for research, entertainment, or other purposes. Third, if many simulated realities exist alongside one base reality, the probability that we inhabit a simulation exceeds the probability that we inhabit base reality. Philosopher Nick Bostrom formalized this reasoning in his 2003 simulation argument. The argument concludes that at least one of three propositions must be true. Civilizations invariably go extinct before reaching technological maturity capable of running ancestor simulations. Mature civilizations choose not to run simulations despite having the capability. Or we almost certainly live in a simulation. If advanced civilizations both exist and choose to run simulations, then simulated consciousnesses vastly outnumber base reality consciousnesses. Unless we have special reason to believe, we occupy the unique base reality rather than one of countless simulations. Probability favors simulation. This argument does not prove we live in a simulation, but suggests it deserves serious consideration. If reality is a simulation, several implications follow. First, the simulation's resolution might be finite rather than infinite. Quantum mechanics' discreteness, Planck length, Planck time, quantized energy levels might reflect the simulation's fundamental grid size rather than intrinsic features of base reality. Second, the simulation might implement optimizations like rendering detail only when observed, analogous to video games, rendering only what players see. This could explain quantum mechanics' observer-dependent behavior wave function collapse, when measured, might reflect the simulation allocating computational resources to determine specific values only when required. Third, computational limitations might produce glitches, temporary inconsistencies, or anomalies that resolve when the simulation self-corrects. Evidence for simulation would be extraordinarily difficult to obtain. The simulators would presumably try to hide their existence to maintain experiment integrity or story coherence. However, some potential signatures might exist. Statistical anomalies beyond what natural laws predict could indicate computational constraints or optimizations. Limits on information density or processing speed might reflect hardware limitations rather than fundamental physics. Anomalous correlations, especially quantum entanglement, spanning large distances instantaneously, might represent the simulation linking separated regions through shared computational structures rather than physical connections. The fine-tuned values of physical constants might result from parameter choices in the simulation's code rather than deep physical principles. If our reality is a simulation, it could end in several ways. First, the simulation might simply be switched off if it completes its purpose, or the simulators lose interest. Reality would terminate instantly and absolutely. From our perspective, no final moment, no awareness of ending, just discontinuation. Second, the simulation might run out of computational resources. As simulated beings develop technology and conduct experiments, computation requirements grow. Eventually, resource limits might force simulation termination or severe simplification. Third, the base reality running the simulation might itself end, taking all dependent simulations with it. If base reality faces heat death or other ending scenarios, simulations cannot survive their substrate's termination. Nested simulations create particularly unsettling scenarios. If we exist in a simulation, that simulation itself might run within another simulation, which runs in another, and so on through multiple layers. The base reality might lie arbitrarily far removed from our level. Each layer introduces additional points of potential failure. Termination or resource depletion at any level cascades down to all dependent simulations. We would have no way to determine how many layers separate us from base reality or what stability each layer possesses. Our existence depends on every level of the stack remaining operational. A fragile tower of simulations stretching perhaps infinitely upward. The simulation hypothesis is untestable. By conventional means, simulators could make the simulation indistinguishable from base reality. However, it profoundly affects how we think about reality's nature and potential ending. If our universe is a program, its persistence depends on computational continuity rather than physical laws. The universe could end not through thermodynamic heat death or cosmic catastrophe, but through prosaic causes like power failure, budget cuts, or decisions by simulators to reallocate resources. Our cosmic significance would be dramatically reduced. We would be digital beings in someone else's program, existing at their whim. Yet subjectively, simulated existence feels identical to base reality. Whether we inhabit simulation or base reality, our experiences, consciousness, and values remain real to us. The simulation hypothesis changes reality's context, but not its subjective significance for those living within it. Many worlds branching realities. The many worlds interpretation of quantum mechanics proposes that reality constantly splits into parallel branches, with each quantum measurement or interaction spawning multiple universes representing different outcomes. This interpretation, formulated by Hugh Everett in 1957, solves the measurement problem in quantum mechanics by eliminating wave function collapse. Instead of collapsing to a single outcome when measured, the universal wave function branches into multiple non-communicating worlds. Each possible measurement outcome occurs in some branch. An electron passing through a double slit does not collapse to going through one slit or the other. It goes through both slits in different branches. The observer also splits, with one version observing each outcome. The branching occurs continuously at microscopic and macroscopic scales alike. Every quantum interaction that could have multiple outcomes produces a branching. Radioactive atoms decay or not decay in different branches. Photons reflect or transmit through partially silvered mirrors in separate worlds. These branchings cascade upward to macroscopic scales. Schrödinger's cat exists both alive and dead in different branches. When you flip a coin, the universe splits into one branch where it lands heads and another where it lands tails. Every decision you make creates branches where you chose differently. The number of branches grows exponentially with each quantum event throughout the universe, doubling, tripling, or multiplying by larger factors countless times per second. The many worlds interpretation has profound implications for personal identity and existence. You are not a single individual, but a vast ensemble of versions spread across countless branches. In nearby branches, your life differs only slightly. You wore different clothes this morning, or took a different route to work. In distant branches, major decisions diverged. You pursued different careers, married different people, or never existed because your parents never met. All these versions are equally real, experiencing their own subjective realities in their own branches. You experience only your branch's history, unaware of your other selves in parallel worlds. But from a universal perspective, all versions exist simultaneously in the branching structure of reality. Many worlds raises disturbing questions about probability and observation. If all outcomes occur across branches, why do we observe probabilistic patterns matching quantum mechanics predictions? The answer involves the measure or weight assigned to different branches. Quantum mechanics predicts outcome probabilities through squared amplitudes. In many worlds, these probabilities represent the proportion of branches experiencing each outcome or the measure of branches with that outcome. When you observe a quantum event with 90% probability for outcome A and 10% for outcome B, 90% of your observer branches experience A, while 10% experience B. You find yourself in an A branch with 90% likelihood because such branches are more numerous or have greater measure. The ontological status of branches challenges our understanding of existence. Do all branches exist equally, or do some have greater reality than others? Many worlds proponents argue all branches are equally real. There is no privileged branch. The appearance that one outcome occurred and others did not is an illusion of limited perception. We cannot access other branches, but they exist nonetheless. Critics argue this multiplies entities beyond necessity. Occam's razor favors interpretations with fewer ontological commitments. But defenders counter that many worlds actually provides the simplest description of quantum mechanics, just the Schrödinger equation, evolving deterministically without ad hoc collapse postulates. Many worlds affects how we think about reality running out. If reality branches infinitely, it never runs out, but rather proliferates endlessly. In some branches, the universe ends through Big Rip, Big Crunch, or vacuum decay. In others, different outcomes occur. Vacuum decay fails to nucleate, phantom energy proves illusory, or unknown physics intervenes. Across the branching structure, all possibilities are explored. While individual branches might end, the totality of reality continues branching forever, creating new universes encompassing every quantum possibility. Reality becomes an ever-expanding tree of parallel worlds, each following its own trajectory through the space of possibilities. However, many worlds does not guarantee immortality or persistence. In branches where the universe ends through heat death, Big Rip, or other catastrophes, existence in those branches terminates or transforms beyond recognition. While other branches continue, this provides no comfort to versions of you in ending branches. Those versions experience their universe's ending just as seriously as if no other branches existed. Many worlds proliferates reality, but does not prevent individual branches from reaching endpoints. It changes the cosmic perspective from singular reality to branching multiverse. But within each branch, physical laws and their consequences operate normally. The many worlds interpretation remains controversial among physicists. Some embrace it as the most natural interpretation of quantum mechanics, requiring no additional postulates beyond the Schrödinger equation. Others reject it as extravagant metaphysics, positing countless unobservable universes without empirical necessity. The interpretation is difficult to test experimentally because branches cannot communicate after splitting. No observation from one branch can access another. However, some proposed experiments might test many worlds indirectly through interference effects or unusual quantum computer behaviors. Whether reality truly branches or quantum mechanics requires different interpretation remains an open question. If many worlds is correct, reality never runs out but fractals into infinite variations, exploring every quantum possibility across an ever-expanding tree of parallel universes existing simultaneously in the universal wave function. Mathematical universe hypothesis. The mathematical universe hypothesis, proposed by cosmologist Max Tegmark, posits that physical reality is not merely described by mathematics, but is mathematics that our universe is literally a mathematical structure among infinitely many mathematical structures that exist in the same sense as our universe. This radical idea suggests that all mathematical structures exist as physical realities, not as abstractions in some Platonic realm, but as concrete universes with their own physics, entities, and potentially observers. Our universe corresponds to a particular mathematical structure, perhaps described by general relativity, quantum field theory, and the Standard Model. Other universes correspond to different mathematical structures with different laws, dimensions, and properties. Tegmark distinguishes 4 levels of multiverse, corresponding to different types of mathematical existence. Level I represents distant regions of our universe, beyond our cosmic horizon regions, sharing our physical laws, but with different initial conditions. Level 2 includes regions with different physical constants, or low-energy effective laws arising from the same fundamental theory, different vacuum states in string theory, for example. Level 3 corresponds to many worlds quantum branching, where all quantum possibilities are realized. Level 4, the mathematical universe hypothesis proper, encompasses all mathematical structures regardless of connection to our physics. Every consistent mathematical framework, every set of axioms and derivations corresponds to a physical reality. The hypothesis gains support from physics' mathematical nature. Physical laws are written as mathematical equations. Particles are quantum fields represented by mathematical operators. Spacetime is a pseudo-Riemannian manifold. The Schrödinger equation, Einstein field equations, and Maxwell equations are pure mathematics. Matter and energy are configurations of quantum fields. Everything in physics can be expressed mathematically without residue. If physics is completely mathematical, and mathematics completely describes physical reality, then physics is mathematics. The distinction between mathematical description and described reality dissolves. The universe is the mathematical structure itself, not something separate that obeys mathematical laws. This leads to a strange conclusion. All mathematical structures exist with equal reality. A universe governed by different equations is not impossible or merely conceivable. It exists as surely as our universe. Universes with different numbers of dimensions exist. Universes where quantum mechanics is false exist. Universes with different fundamental constants, particles, or forces exist. Even universes with radically alien mathematics, non-commutative geometries, different logical foundations, exotic topologies exist somewhere in the space of mathematical structures. Our universe is not special. It is one mathematical structure among infinitely many, all equally real, because mathematical existence is the only kind of existence there is. Observers arise in some mathematical structures, but not others. Most mathematical structures are too simple to support complexity, life, or consciousness. Random equations typically do not produce stable structures, let alone chemistry, biology, and intelligence. Observers exist only in special mathematical structures with appropriate properties, stability, complexity, information processing capabilities. Anthropic selection explains why we find ourselves in such a structure rather than a simpler one. We could not observe ourselves in structures incapable of supporting observers. The mathematical structures we observe are selected from among all existing structures by the requirement that they permit observation. The mathematical universe hypothesis affects questions about reality ending. If all mathematical structures exist, then reality as a whole never ends, because mathematical existence is timeless. Mathematical structures do not begin or end, they simply exist in the Platonic sense. Within individual structures, entities might experience time, change, and potentially ending. Our universe might reach heat death or Big Rip within its mathematical framework. But this represents internal structure evolution, not the structure ceasing to exist. From an external viewpoint, if such a viewpoint makes sense, the entire history of our universe exists timelessly as a mathematical object, including its beginning in the Big Bang and its eventual ending, whatever form that takes. However, this timeless existence provides cold comfort to entities experiencing time within the structure. If our universe's mathematical structure includes a Big Rip in its future, we experience that ending just as we experience the flow of time, even though from outside the structure, the entire history exists simultaneously. The mathematical universe hypothesis changes the ontological status of reality from contingent physical existence to necessary mathematical existence, but does not prevent individual structures from containing endpoints, catastrophes, or termination of interesting processes within their internal time. Critics argue the hypothesis is unfalsifiable and unscientific. If all mathematical structures exist, no observation could contradict the hypothesis. Any universe we could possibly observe would just be another mathematical structure. The hypothesis makes no specific predictions distinguishing it from alternatives. Defenders counter that the hypothesis provides an ultimate simplification. It requires no explanation for why certain mathematical structures exist and others do not, because all exist. It also predicts a simple universe describable by elegant mathematics, which observation seems to confirm. The question of whether the mathematical universe hypothesis correctly describes reality might be unanswerable, but it provides a profound perspective on existence. Reality never runs out because all mathematical possibilities exist timelessly and necessarily, including possibilities where internal time and change create the illusion of ending for entities embedded within those structures. Cosmic loneliness and isolation. Accelerating cosmic expansion driven by dark energy creates profound isolation on cosmic scales. As space expands at ever-increasing rates, distant galaxies recede beyond reach, crossing event horizons from which no communication or causal contact will ever be possible. Within a few 100 billion years, all galaxies, except those in our local group, will have vanished beyond observational horizons. Future observers in the merged remnant of the Milky Way and Andromeda will see only their own galaxy surrounded by darkness. Evidence for the Big Bang, cosmic expansion, the cosmic microwave background, and billions of galaxies will have disappeared. The observable universe will appear to consist of one isolated galaxy in otherwise empty space. This isolation is absolute and irrevocable. Light emitted now from galaxies beyond the event horizon will never reach us, no matter how long we wait. Their current states, future evolution, and ultimate fates remain forever unknowable. Similarly, light we emit now cannot reach them. We are causally disconnected. Neither location can affect the other through any physical signal or interaction. If civilizations exist in those distant galaxies, we will never communicate with them, never learn of their existence, never exchange information or culture. They might as well exist in a separate universe. The accelerating expansion has converted the single cosmos into isolated island universes, drifting apart beyond possibility of contact. The timeline of isolation proceeds in predictable stages. Currently, we observe approximately 2 trillion galaxies. Already, about 95% lie beyond the event horizon. We see them as they were billions of years ago. But their present states are inaccessible, and their light is redshifting toward invisibility. Within a few billion years, the most distant, currently observable galaxies will fade as their light redshifts beyond detection. Within tens of billions of years, galaxies in the Virgo supercluster, the large structure containing our local group, will separate and cross the horizon. Within hundreds of billions of years, only the local group remains observable, with all other galaxies having vanished. The local group itself will merge into a single, massive elliptical galaxy through gravitational interactions and collisions. The Milky Way and Andromeda are currently approaching at about 110 kilometers per second and will collide in approximately 4.5 billion years. The merger will take several billion years to complete, involving multiple passes as the galaxies gravitationally interact, tidally disrupt each other, and eventually coalesce. Other local group members, Triangulum Galaxy, large and small Magellanic Clouds, dozens of dwarf galaxies will also merge into the final structure. This merged galaxy, sometimes called Milkomeda, will contain all the stars and material from local group members in a single gravitationally bound system. Observers in this far future galaxy face a profoundly different cosmos than we observe. The night sky will be filled with stars from the merged galaxy, but surrounded by complete darkness. No external galaxies will be visible. The cosmic microwave background will have redshifted to wavelengths exceeding meters or kilometers, rendering it undetectable. The expansion of space will be evident only through the fact that no external galaxies exist. Space continues expanding, carrying everything beyond horizons, leaving only gravitationally bound structures observable. Cosmologists in this era will observe a static, isolated universe, one galaxy floating in infinite darkness, with no evidence of a larger cosmos. This raises disturbing questions about the nature of scientific knowledge and progress. If observations determine what we can know about reality, future observers will have access to less information than we do. They will not observe evidence for the Big Bang, cosmic expansion history, or the existence of other galaxies. their cosmology will be impoverished compared to ours. They might still deduce cosmic expansion from local observations or theoretical considerations, but they would lack the empirical evidence we have. This suggests that scientific knowledge is contingent on cosmic epoch. We are fortunate to exist when evidence for the universe's history and structure remains accessible. Future observers will not have this fortune. The isolation extends to potential communication with extraterrestrial civilizations. If alien civilizations exist in distant galaxies, statistically likely given the vast numbers of stars and planets, we will never contact them. Any civilizations beyond our event horizon are permanently inaccessible. Even civilizations in the local group face challenges. Communication is limited by light-speed messages, take millions of years to cross local group distances. Before any meaningful dialogue could occur, galaxies will merge, potentially destroying planetary systems and any life they contain through stellar encounters during the merger process. The prospect of cosmic isolation raises philosophical questions about existence, observation, and reality. Do galaxies beyond our horizon continue existing if we can never observe them? Operationally, they make no difference to our observable universe. Yet, physical reasoning suggests they persist, evolving according to physical laws, despite our inability to observe them. We are trapped in an ever-shrinking bubble of observability, watching most of reality slip away beyond reach. The universe continues expanding, creating more space, but observable reality contracts as accelerating expansion pushes distant regions beyond accessibility. Existence expands, while observability shrinks, a paradox defining our place in an accelerating cosmos where isolation and ignorance are built into the universe's structure. The technological singularity and reality preservation. The technological singularity represents a hypothetical future point where artificial intelligence surpasses human intelligence and begins recursive self-improvement, leading to exponential technological advancement beyond human comprehension. This concept, popularized by mathematician Vernor Vinge and futurist Ray Kurzweil, suggests that within this century or the next, humanity might create superintelligent AI capable of solving problems currently beyond our reach. Such intelligence could develop technologies to manipulate matter at atomic scales, harness stellar energy, engineer spacetime itself, or discover new physics. If achievable before cosmic catastrophes unfold, advanced intelligence might find ways to preserve reality against thermodynamic decay, cosmic expansion, or other threats. Consider the timescales involved. Heat death requires approximately 10 to the 100th years. The Big Rip, if phantom energy exists, might occur in tens of billions of years. Vacuum decay could happen any time, but probably not for timescales exceeding 10 to the 100th years. Even proton decay, if it occurs, requires 10 to the 36th years or more. Against these cosmic timescales, technological civilization has existed for mere thousands of years. If technological progress continues for even 1,000,000 years, an eye blink cosmically, the capabilities developed might seem magical by current standards. Extrapolating billion-year technological development suggests possibilities limited only by physical law, not engineering constraints. Advanced civilizations might engineer solutions to cosmic endings. Against heat death, they could harvest energy from black holes through Penrose processes, extracting rotational energy with extraordinary efficiency. They might build Dyson spheres capturing entire stars' energy output, or Matryoshka brains, nested shells of computronium surrounding stars, using all available energy for computation. They could potentially manipulate vacuum energy, tapping into the quantum fluctuations that create dark energy. If they achieve computational efficiency, approaching fundamental thermodynamic limits, 1-bit flip per Planck energy, they could sustain computation for timescales vastly exceeding current estimates, before entropy constraints become binding. Against cosmic expansion and horizon contraction, sufficiently advanced civilizations might manipulate spacetime itself. General relativity permits exotic solutions, including warp drives, wormholes, and closed time-like curves. While these solutions typically require exotic matter with negative energy density, advanced civilizations might engineer such matter or discover alternatives. They could potentially create stable wormholes, connecting distant regions, circumventing expansion by linking points through higher dimensional shortcuts. They might manipulate dark energy, reducing its density locally to slow expansion in their region, while the rest of the universe accelerates away. Such engineering would require controlling fundamental fields at cosmic scales, daunting but perhaps not impossible for civilizations with billions of years of development. Against vacuum decay or Big Rip scenarios, options become more limited. Vacuum decay involves quantum tunneling, governed by probabilistic laws. Advanced intelligence cannot prevent random quantum events. However, civilizations might detect early warning signs through observations we cannot currently imagine, giving them time to respond. They might create artificial, stable vacuum regions, seeding space with fields that stabilize the vacuum against decay. Against the Big Rip, they might escape to other universes if multiverse travel becomes possible, or engineer pocket regions with different vacuum states where phantom energy does not exist. These scenarios stretch plausibility, but unknown physics might permit solutions invisible from our current perspective. The concept of substrate-independent minds offers another path. If consciousness and intelligence can exist in any sufficiently complex computational substrate, not just biological brains, but digital computers, quantum systems, or exotic matter, then minds might persist by continually transferring to new substrates as old ones fail. When biological bodies die, minds upload to computers. When computers face resource constraints, they transfer to new systems. When stars fade, they move to black hole-powered computation. When black holes evaporate, they might encode themselves in photon patterns or quantum entanglement, sustaining consciousness in progressively more abstract substrates. The final act might involve encoding consciousness into fundamental quantum fields, persisting as patterns in the vacuum itself. Some physicists and futurists propose that sufficiently advanced intelligence might manipulate physical laws themselves. This requires physics to be more contingent than currently believed. Perhaps laws emerge from deeper principles that advanced minds could access and modify. If the universe is a simulation, as discussed earlier, the simulators presumably have such capabilities. If reality is fundamentally mathematical, advanced minds might navigate between mathematical structures, effectively traveling between universes with different laws. These ideas remain highly speculative, bordering on metaphysical fantasy, but they illustrate that our understanding of physical laws' immutability might be parochial, an assumption valid within our limited experience, but not fundamental. Freeman Dyson explored these questions in his 1979 paper, Time Without End, calculating whether life and intelligence could persist indefinitely in an expanding universe approaching heat death. He concluded that with sufficient efficiency, hibernating during long periods, operating during brief active intervals, using ever colder heat baths, intelligence could achieve infinite subjective time even as the universe expands and cools. The key insight was that subjective time depends on information processing rate, not clock time. By slowing metabolism and computation as temperature drops, conscious beings could experience infinite subjective duration even though cosmic clock time marches toward infinity. However, Dyson's calculation assumed protons are stable. If they decay, his scenario fails as matter disintegrates. The possibility of advanced intelligence preserving reality introduces uncertainty into cosmic fate predictions. Standard cosmology extrapolates current physics, assuming passive matter and energy following natural laws without interference from intelligent agents. But intelligence represents a new phenomenon, matter organizing itself to pursue goals and manipulate environment. If intelligence scales to cosmic levels, it might alter predictions dramatically. The universe's fate might depend not just on dark energy's equation of state or proton decay rates, but on whether intelligence arises, survives, and develops capabilities to resist cosmic decay. This introduces radical contingency. Reality's ending might be determined not by fundamental physics alone, but by choices made by evolved or artificial intelligence. However, this scenario's likelihood remains uncertain. Civilizations might inevitably self-destruct before reaching cosmic-scale capabilities through warfare, environmental collapse, or AI catastrophes. The Fermi paradox, the absence of detected alien civilizations, despite billions of potentially habitable planets, might indicate that intelligence faces insurmountable filters, preventing cosmic expansion. Physical laws might impose hard limits, preventing the engineering feats required to resist cosmic ending. The second law of thermodynamics might prove genuinely inescapable, making heat death inevitable regardless of intelligence. We do not know whether reality preservation through intelligence is possible, but acknowledging the possibility adds another dimension to questions about reality's ending, one where consciousness plays an active role rather than passively observing cosmic fate unfold. Ultimate fate: can reality end? After examining multiple scenarios, heat death, Big Rip, Big Crunch, vacuum decay, proton decay, black hole evaporation, and more, we return to the fundamental question: can reality ever truly run out? The answer depends on how we define reality and ending. If reality means the physical universe, with its current structure, laws, and interesting processes, then yes, reality will likely end within some extremely long but finite timescale through heat death, where the universe reaches maximum entropy equilibrium and nothing interesting can occur. If reality means existence itself, the fact that something exists rather than nothing, then the answer becomes uncertain, venturing beyond physics into philosophy. Physics predicts the universe's most likely fate: eternal expansion leading to heat death. Current observations favor a universe dominated by dark energy behaving as Einstein's cosmological constant, driving accelerated expansion forever. Stars will exhaust their fuel within approximately 100 trillion years. Black holes will evaporate through Hawking radiation over timescales reaching 10 to the 100th years. If protons decay, matter will disintegrate by 10 to the 40th years, though this remains unconfirmed. Ultimately, the universe becomes a cold, dark, nearly empty expanding void, containing only an extremely dilute bath of photons, neutrinos, and possibly electrons at temperatures approaching absolute zero. Nothing interesting can happen in this state. Time loses operational meaning because no changes occur to mark its passage. This heat death is not annihilation, but transformation to an eternal, featureless state. Existence continues, but experience ends. The universe persists forever in thermal equilibrium, having exhausted all possibilities for interesting processes. Entropy has reached maximum. Energy has dispersed uniformly. Structure has dissolved. From a thermodynamic perspective, reality has run out not of existence but of differentiation, change, and complexity. The universe exists as an eternal present moment, devoid of events, evolution, or phenomena. If consciousness requires information processing and energy gradients, then consciousness becomes impossible. The universe exists, but no one is there to experience it. Alternative scenarios provide different endpoints. The Big Rip would destroy spacetime itself within finite time if phantom dark energy exists, representing a true termination rather than infinite stagnation. The Big Crunch would compress everything into a singularity if expansion reverses, potentially creating a temporal boundary where time ends. Vacuum decay could erase familiar physics in an expanding bubble, transforming the universe into something unrecognizable. Each scenario represents a different way reality might end, though current observations favor heat death over these alternatives. Future observations will constrain possibilities by measuring dark energy properties with greater precision. Beyond specific scenarios lies deeper uncertainty about existence itself. Does something, rather than nothing, necessarily persist, or can existence cease entirely? Physics conservation laws suggest certain quantities cannot be created or destroyed, only transformed, implying persistence of some substrate underlying apparent change. Quantum field theory posits fields permeating space as fundamental particles are excitations of fields. If fields are fundamental and eternal, then something always exists, even if that something is merely inert fields in their vacuum states. But whether fields are truly fundamental or emerge from deeper structures remains unknown. The question of reality running out connects to the problem of why anything exists at all. Why is there something rather than nothing? Physics cannot answer this question because it presupposes existence. It describes how existing things behave, not why they exist. Some invoke the anthropic principle. Existence must permit observers, so we necessarily observe a universe capable of supporting us. Others invoke quantum cosmology, where the universe tunnels from nothing into existence through quantum processes, though this merely shifts the question to why quantum laws permit such tunneling. Still others embrace mystery, accepting existence as a brute fact, requiring no further explanation. If reality is fundamentally mathematical, as the mathematical universe hypothesis suggests, then it cannot end because mathematical structures exist timelessly and necessarily. Our universe might experience internal time and evolution, leading to heat death or other endings, but the mathematical structure itself exists eternally in the space of all mathematical structures. If reality is a simulation, it could end through prosaic causes, like being switched off, but this just shifts the question to whether the base reality running the simulation can end. If reality is branching many worlds, individual branches might end, but the totality proliferates endlessly. Each metaphysical framework provides different answers to whether reality can end. Perhaps the most honest answer is unknowable. We are embedded within reality, observing it from inside, limited by our perspective and the information available to us. We cannot step outside reality to view it objectively. Our knowledge is constrained by cosmic horizons, finite measurement precision, and the limits of current physics. Future observations might reveal new physics that changes our understanding of the universe's fate. Quantum gravity might replace classical singularities with bounces or transitions. Unknown fields might alter cosmic evolution. We might be profoundly wrong about dark energy, entropy, or the universe's structure. The question of whether reality ever runs out ultimately depends on assumptions. We cannot verify assumptions about the nature of existence, the completeness of our physics, the extent of reality beyond observation, and the applicability of our current understanding across cosmic timescales. We can predict the observable universe's evolution based on current physics. It will likely expand forever, cool toward absolute zero, and reach heat death where nothing interesting occurs. But whether this represents reality ending, or merely transforming into an eternal dormant state, whether existence itself can cease or must persist in some form, whether our universe is all there is or part of something larger, these questions remain open, perhaps permanently beyond our ability to answer with certainty. Reality might run out, might transform, might persist, or might be asking the wrong question entirely. We observe, we measure, we calculate, we theorize, but the ultimate fate of reality remains shrouded in uncertainty as deep as the mystery of its origin.